Have you ever stared up at the night sky and wondered what it would be like to step through a doorway to another galaxy, or even another time? Picture a tunnel weaving through the fabric of space itself, a cosmic shortcut where the rules of physics, as we know them, begin to bend and twist. These are wormholes, one of the most tantalizing and mysterious concepts in all of science, and they just might hold the key to unlocking the deepest secrets of the universe. From the far reaches of theoretical physics to the wild frontiers of human imagination, the idea of traversable wormholes has captivated scientists, storytellers, and dreamers alike, suggesting that the vast distances between stars could one day be crossed in the blink of an eye. Today, we're setting off on a journey to explore 30 incredible theories about wormholes and space-time travel ideas that will challenge everything you think you know about reality, time, and our place in the cosmos. Some of these concepts are rooted in the equations of general relativity, first proposed by Albert Einstein himself, while others spring from the minds of visionary physicists daring to ask, what if? What if we could use wormholes not only to travel across space but to journey into the past or future? What if these cosmic tunnels are hiding in plain sight, woven into the very structure of the universe? And what if humanity's greatest adventures are yet to come, on the other side of a gateway we have yet to discover? This isn't just a tour of far-out ideas, it's an invitation to expand your mind and reimagine what's possible. Whether you're a long-time space enthusiast or simply curious about the mysteries that lie beyond our world, you're about to embark on an exploration that blends cutting-edge science with boundless curiosity. We'll dive into theories that range from the well-established to the wildly speculative, each one offering a new perspective on how we might one day breach the limits of space and time. So settle in, open your mind, and get ready, because by the time we're done, you may never look at the night sky the same way again. Our journey begins not with wild speculation, but with the solid foundation of mathematics. The very first theory of wormholes emerges directly from the equations of Albert Einstein's theory of general relativity, a set of ideas that forever changed our understanding of gravity, space, and time. In 1915, Einstein showed us that what we perceive as gravity is actually the warping, the bending, of the fabric of spacetime itself by mass and energy. Think of it like this: if you place a heavy bowling ball in the center of a taut rubber sheet, it creates a deep indentation. Now, if you roll a smaller marble near that curve, it will spiral inward, not because of a mysterious force, but simply because it's following the curvature created by the bowling ball. Planets and stars warp the cosmos in a similar way, but it was 2 decades later, in 1935, that Einstein and his colleague, physicist Nathan Rosen, explored a fascinating implication of these equations. They were working on a model to describe fundamental particles like electrons using only spacetime geometry, a concept known as the geometrodynamics program. In doing so, they discovered that the math allowed for something extraordinary: a bridge. Their solution described a structure that could connect 2 separate, distant regions of flat spacetime through a tunnel-like throat. This wasn't science fiction, it was a legitimate, if highly theoretical, prediction of their own physical laws. We now call this structure an Einstein-Rosen Bridge, the original scientific name for a wormhole. The most common way to visualize this is with a simple piece of paper. Picture our universe as a flat, 2-dimensional sheet. 2 points on that sheet might be very far apart if you travel across the surface. But if you could bend the paper so those 2 points touch, and then you punch a pencil through the fold, you've created a shortcut, a tunnel that bypasses the long journey across the surface. In 3-dimensional space, this tunnel is often depicted as an hourglass shape, with 2 wide, flaring mouths connected by a narrow, cylindrical throat. One mouth could be here in our solar system, while the other could be in a galaxy millions of light years away. In theory, an object could enter one mouth, and if the tunnel is stable, exit the other almost instantly, having effectively traveled faster than light without ever locally breaking the universal speed limit. However, Einstein and Rosen's original bridge had a tragic flaw, a characteristic that made it useless for any kind of practical travel. This theoretical tunnel was incredibly unstable. It would form, snap shut, and disappear in an instant far too quickly for even a single photon of light to make the trip through. The gateway would collapse into a singularity, a point of infinite density, effectively sealing off the passage. So while the mathematics gave us the breathtaking idea of a cosmic shortcut, it also seemed to immediately slam the door shut on it. But this crucial first step opened the minds of physicists to a world of possibilities, proving that the fabric of reality might be far more interconnected and strange than we ever dreamed. For decades after Einstein and Rosen, the wormhole remained a mathematical curiosity, a fascinating idea that seemed forever out of reach, a bridge designed to collapse the moment you set foot on it. The dream of a traversable wormhole, one you could actually journey through, required a radical new way of thinking. That crucial leap forward arrived in 1988, thanks to the work of physicists Michael Morris and Kip Thorne. Their groundbreaking theory didn't just tweak the old model, it completely reimagined the problem. Instead of asking if the equations of general relativity allowed for wormholes, they flipped the script. They started with a wish list for the perfect interstellar shortcut and worked backward to figure out what physical laws would be required to build it. Morris and Thorne outlined the precise engineering specifications for a stable, human-passable wormhole. They described a symmetric tunnel with a spherical mouth, a smooth, wide throat to prevent travelers from being crushed by tidal forces, and a design that ensured the journey would be brief and safe. This wasn't just theoretical play, it was a serious effort to map the boundary between known physics and the fantastical. Their work provided a detailed blueprint, and in doing so, they identified the single biggest hurdle to making it a reality. The throat of the wormhole wants to collapse. To prop it open, to keep that gateway from snapping shut, you would need to line the throat with something truly bizarre, a substance known as exotic matter. This isn't just unusual material. Exotic matter defies the everyday rules that govern our universe. Specifically, it would need to possess something called negative energy density, which results in a gravitational repulsion. Think about gravity for a moment. Everything with mass or energy that we've ever observed creates positive energy density, which warps spacetime inward, attracting other objects. This is why planets have gravity. Exotic matter would do the exact opposite. It would generate a kind of anti-gravity, pushing spacetime outward. Inside a wormhole's throat, this repulsive force would act as a counterpressure against the immense gravitational pull trying to crush the tunnel closed, effectively serving as cosmic scaffolding. The search for this mysterious substance leads us to some of the strangest corners of quantum mechanics. While we've never collected a jar of exotic matter, the universe does offer glimpses of its possibility through verified quantum phenomena. The Casimir effect is a prime example. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will experience a faint but measurable force pulling them together. Why? Because the space between the plates restricts the kinds of quantum fluctuations that can occur there, while the space outside the plates remains rich with them. This creates a pressure differential, and the mathematical description of the energy between those plates does, in fact, show a negative energy density. It's a tiny, microscopic effect, but it demonstrates that the concept isn't entirely forbidden by physics. The challenge, of course, is one of scale. The Casimir effect produces a minuscule amount of negative energy. To stabilize a wormhole throat large enough for a spaceship, you would need an astronomical quantity of this exotic material, and we currently have no idea how to produce or contain it. Some theories suggest that dark energy, the mysterious force accelerating the expansion of the universe, might share properties with the exotic matter needed for wormholes, but this remains highly speculative. The Morris-Thorne model transformed wormholes from impossible mathematical artifacts into a thrilling engineering challenge. It gave us a target, a set of physical requirements to strive for, and in doing so, it cemented the traversable wormhole as a central pillar of modern theoretical physics and our dreams of reaching the stars. But if the Morris-Thorne wormhole is a grand, cosmic superhighway engineered for future travelers, then our next theory suggests the universe might be paved with an infinite number of microscopic back alleys. This brings us to one of the most profound and mind-bending concepts in all of physics, the idea of quantum foam. To understand this, we have to venture down to the very smallest possible scales, to a realm where the intuitive, smooth universe we experience completely breaks down and is replaced by a seething, chaotic froth of raw potential. This is the domain where quantum mechanics and gravity collide, and it was the brilliant physicist John Wheeler who first gave this chaotic underworld a name and a terrifyingly beautiful image. Wheeler proposed that if we could peer down at the fabric of spacetime at scales as unimaginably small as the Planck length, that's about 1.6 times 10 to the negative 35 meters, we wouldn't see a smooth, continuous geometry. Instead, we would witness a turbulent, chaotic foam. In this foam, the very concepts of before and after, or here and there, lose all meaning. Spacetime itself becomes undefined, fluctuating wildly. And within this frenetic energy, Wheeler suggested, tiny wormholes are constantly blinking into and out of existence. They form, connect two random points for a fleeting instant, and then vanish, all in a timescale so short it makes a nanosecond look like an eternity. This incredible phenomenon is directly linked to another bizarre quantum concept you may have heard of: virtual particles. The Heisenberg uncertainty principle tells us that empty space, a perfect vacuum, is never truly empty. At the quantum level, there is always a fundamental uncertainty in the amount of energy present at any point. This allows pairs of virtual particles and antiparticles to spontaneously erupt into existence, borrowing energy from the vacuum before almost immediately annihilating each other and paying that energy back. This isn't just a theory. We can observe its effects, like in the Casimir effect we discussed earlier. John Wheeler's genius was to apply this same principle of fleeting, energetic fluctuation not just to particles, but to the very geometry of spacetime itself. So, in this view, a wormhole isn't necessarily a rare cosmic anomaly waiting to be discovered. It might be an utterly common, fundamental feature of reality's infrastructure. The universe could be saturated with these Planck-scale wormholes, a dynamic, ever-changing network of tunnels stitching the cosmos together at its most fundamental level. They would be the geometric equivalent of virtual particles, tiny, temporary bridges in the foam. For a moment so brief it's almost meaningless, a tunnel might connect your coffee mug to a random atom in a distant galaxy, only to disappear before any information or matter could possibly traverse it. This leads to a fascinating and deeply philosophical question: could these quantum wormholes ever be scaled up? Is our dream of a traversable wormhole merely a matter of finding a way to capture one of these fleeting quantum events and inflate it, stabilizing it with exotic matter before it winks out of existence? Or is the quantum foam wormhole an entirely separate class of object, forever locked away in the microscopic realm? A hidden layer of cosmic connectivity that we can describe with equations but might never actually touch or see. Wheeler's theory doesn't provide a practical roadmap for travel, but it does something perhaps more important. It fundamentally changes our perception of the universe from a static stage upon which events unfold into a dynamic, bubbling, and intrinsically interconnected entity, forever knitting itself together and pulling itself apart in a dance of breathtaking complexity. Yet this strange feature of Einstein's universe, while fascinating, is not quite time travel. You can't go back and shake hands with your younger self. You can only fast forward into someone else's future. But what if we could find a way to bend this one-way street into a loop? This is where the wormhole enters the picture, not just as a bridge through space, but as the key component for the ultimate machine, a time machine. The concept hinges on taking the natural time dilation effects we just described and locking them into the two ends of a traversable wormhole, creating a permanent, navigable rift in time itself. Imagine we have a stable Morris-Thorne wormhole. For the sake of our thought experiment, let's say it was created or discovered with both mouths sitting right here on Earth, synchronized to the same precise time. They are two gateways sharing a single present moment. Now we decide to take one of these mouths on a journey. We load it onto an incredibly fast-moving spaceship, one capable of traveling at a significant fraction of the speed of light, and send it screaming out into the cosmos and back. According to special relativity, time for that traveling mouth will pass much more slowly than it does for the mouth that remained safely on Earth. From the perspective of someone on Earth, decades might pass. But for the mouth on the ship and for any clock traveling with it, only a few years might go by. Here is the pivotal moment. The ship returns and lands. We now have our two wormhole mouths sitting side by side again, but they are no longer synchronized. The mouth that stayed on Earth is decades older than the mouth that went on the journey. Because the wormhole is a direct tunnel through space-time, this time difference is now a fixed, permanent feature of its structure. If you were to step into the mouth that remained on Earth, the older mouth, you would instantly exit from the younger mouth that just returned from its journey. You haven't just moved through space, you have stepped decades into the past relative to the current time on Earth. Conversely, if you stepped into the younger mouth, you would exit from the older mouth, effectively jumping years or decades into the future. This creates a breathtaking possibility, a closed time-like curve. This is the technical term for a path through space-time that loops back onto itself, allowing an object to return to its own past. You could, in theory, walk through the wormhole and arrive at a location and time before you even left. The implications are as staggering as they are bewildering. You could witness historical events firsthand, or perhaps even interact with them, raising all the classic paradoxes we know from science fiction. What if you prevented your own parents from meeting? This is the famous grandfather paradox, and it presents a serious logical conundrum that physicists and philosophers grapple with. An alternative method to achieve the same effect relies not on high speed, but on immense gravity, using the time dilation predicted by general relativity. Instead of sending one mouth on a fast journey, you could carefully lower it down into the incredibly intense gravitational field near a neutron star or a black hole. Time flows far slower in such a powerful gravitational well, after leaving it there for a set period, while the other mouth remains in a region of weak gravity like Earth. You then retrieve it. The result is the same, a permanent time difference between the two connected mouths, creating a gateway to the past via one entrance and the future via the other. The sheer audacity of this theory is what makes it so compelling. It isn't mere fantasy. It's a direct, logical consequence of combining the known laws of relativity with the theoretical structure of a traversable wormhole. It suggests that if the incredible engineering challenges of creating and stabilizing a wormhole could ever be overcome, the power to navigate time might come along with it. However, this doesn't mean the universe makes it easy. Many physicists like Stephen Hawking have proposed that there might be a chronology protection conjecture, a principle of physics that actively prevents closed time-like curves from forming, perhaps through devastating quantum feedback or other unknown mechanisms that would destroy a wormhole the moment it became a time machine. So while the math allows for the possibility, the universe itself might have a final veto. If black holes represent the universe's ultimate one-way street, a point of no return where matter and energy disappear forever, then their theoretical opposite would have to be something just as radical, a point of no entrance, a cosmic fountain from which reality pours forth but can never be entered from the outside. This is the concept of a white hole, a hypothetical object that is, in essence, a black hole playing the film of its life in reverse. And while a white hole has never been observed, its mathematical elegance is so compelling that it has led physicists to a stunning proposal. Perhaps every black hole is secretly connected to a white hole somewhere else, and the tunnel between them is the wormhole we've been searching for all along. To understand a white hole, we first need to revisit the classic description of a black hole. A black hole forms when matter collapses under its own gravity to a point of infinite density called a singularity. This singularity is shrouded by an event horizon, a boundary in spacetime beyond which nothing, not even light, can escape the gravitational pull. The event horizon acts as a one-way membrane. Things can fall in, but according to classical physics, nothing can ever get out. Now, if we take the equations of general relativity that describe this process and literally reverse the direction of time, we get a white hole. Instead of an event horizon that only allows things inward, a white hole would have a horizon that only allows things outward. Matter and energy would erupt from the singularity within, but nothing from the external universe could ever cross the horizon to get inside. This idea naturally leads to a profound question. Where is all the material that falls into a black hole going? The mathematics of an isolated black hole offers no answer. It simply piles up at the singularity. But if we consider the complete, maximally extended solution for a black hole, a mathematical model that describes its entire history from infinite past to infinite future, we find something astonishing. The solution doesn't just describe one universe with a black hole. It describes two separate, asymptotically flat universes connected by a wormhole-like structure called an Einstein-Rosen Bridge. In this model, the black hole in our universe is physically connected to a white hole in another universe. Matter falling into our black hole wouldn't be destroyed. It would be funneled through the throat of this wormhole and then violently ejected out of the white hole into a completely different region of spacetime. This creates a breathtaking cosmic circuit. Our universe gains a black hole, a drain pulling matter in. The other universe gains a white hole, a source spewing new material out. For a brief moment, the wormhole throat is open and passable, acting as a true bridge between worlds. However, this elegant solution comes with its own set of devastating problems. The wormhole connection in this model is not stable or traversable for any meaningful amount of time. It forms and then pinches off faster than any signal or particle could travel through it, severing the connection and leaving behind two separate, disconnected singularities. A black hole in one universe and a white hole in the other. Furthermore, white holes are considered to be tremendously unstable entities. Pouring a vast amount of energy out into a universe would be a violently explosive event, and most physicists believe such an object would almost instantly collapse into a black hole itself if it ever tried to form. Despite these formidable physical barriers, the black hole to white hole wormhole connection remains a powerful and evocative idea. It provides a mathematically consistent picture that avoids the information loss paradox associated with black holes by preserving all the information that falls in. It's just deposited into another universe. Some modern approaches in quantum gravity, like loop quantum gravity, have even revived this concept. They suggest that the extreme quantum effects at the center of a black hole could prevent a true singularity from forming, instead causing a bounce that transforms the black hole into a white hole, effectively turning the entire object into a wormhole to another part of our own universe or another one entirely. In this view, what we see as a supernova or a gamma-ray burst could actually be the final explosive death of a black hole as it transitions into its white hole phase, revealing its hidden tunnel-like nature at the very end of its life. While firmly in the realm of theory, this idea beautifully illustrates how the most exotic objects in our universe might not be endpoints at all, but rather gateways, forever linking the fabric of reality in ways we are only beginning to imagine. This radical idea takes us into one of the most exciting frontiers of modern physics, a proposal so profound it seeks to stitch together the two great pillars of 20th century science, general relativity and quantum mechanics. For decades, these two theories have described our universe with breathtaking accuracy, but they speak entirely different languages. General relativity paints a picture of a smooth, geometric cosmos warped by mass and energy, while quantum mechanics reveals a fuzzy, probabilistic world of chance and uncertainty. Getting them to talk to each other has been the single greatest challenge in physics. Then, in 2013, physicists Juan Maldeissner and Leonard Susskind offered a startlingly elegant dictionary for translation, encapsulated in a deceptively simple equation, ER equals EPR. To unpack this, we need to break down its components. On the left, ER stands for Einstein-Rosen Bridge, the original scientific name for a wormhole. On the right, EPR stands for Einstein-Podolsky-Rosen, named for a famous 1935 paper that highlighted the bizarre, spooky nature of quantum entanglement. Entanglement is the phenomenon where two particles become inextricably linked, their fates intertwined regardless of the distance separating them. Measure the property of one, say its spin, and you instantly know the property of the other, even if it's on the other side of the galaxy. This seems to violate the cosmic speed limit set by light, a notion that so troubled Einstein that he called it spooky action at a distance. Maldeissner and Susskind's breathtaking proposal is that these two concepts, the wormhole and the entangled particles, are not just analogous, they are two different descriptions of the exact same underlying reality. They are, in a deep and fundamental way, identical. An Einstein-Rosen bridge is not a tunnel you could fly through. It is the geometric manifestation of quantum entanglement itself. When two black holes become entangled, the theory suggests, the space between them becomes connected, warping into the tunnel-like structure of a wormhole. The more entangled they are, the shorter and more stable the wormhole becomes. In this view, the fabric of spacetime itself might be woven from a vast, cosmic web of quantum entanglements. This idea finds its strongest support in the holographic principle and Maldeissner's own earlier work on anti-de Sitter space. In this complex mathematical model, a theory of gravity operating in a bulk volume of space is perfectly equivalent to a quantum field theory living on its lower dimensional boundary. It's like a three-dimensional universe being perfectly described by a two-dimensional film projected on its outer surface, a cosmic hologram. Within this framework, if two particles on the boundary are entangled, their connection is represented in the interior geometry as a physical bridge, a wormhole. The quantum information shared between them is encoded as a geometric structure in spacetime. The implications of ER equals EPR are nothing short of revolutionary. It provides a potential geometric solution to the black hole information paradox, a decades-old problem concerning whether information that falls into a black hole is truly lost forever, violating quantum mechanics. If two black holes are entangled, they are connected by a wormhole. Information that falls into one could, in principle, travel through this wormhole and exit the other, thus being preserved. The information isn't lost, it's just somewhere else, maintaining the fundamental rules of quantum theory. This theory completely redefines our understanding of connectivity in the universe. It suggests that what we perceive as empty space is not empty at all, but is instead built from a network of tiny, Planck-scale wormholes, the geometric correlates of countless entangled particles. The vast distance between two stars might be an illusion, a feature of our classical perspective. At the quantum level, they could be intimately connected through the fundamental threads of entanglement, which the ER equals EPR conjecture tells us are the very threads from which the tapestry of spacetime is woven. It's a vision of a universe that is deeply, fundamentally interconnected, where the strange phenomenon of quantum entanglement and the cosmic grandeur of wormholes are ultimately one and the same. While the quantum foam gives us a vision of spacetime seething with microscopic tunnels, and exotic matter offers a theoretical way to prop them open, both present a colossal scaling problem. How could we ever enlarge a fleeting Planck-length wormhole or generate the unimaginable quantities of exotic material needed for a star highway? This is where our next theory introduces a truly cosmic-scale construction crew, one that could have been working since the very first moments of the universe. We're talking about cosmic strings, hypothetical, unimaginably dense threads of pure energy left over from the Big Bang, which could provide the gravitational oomph to not only create wormholes but keep them stable and open for business. To grasp what a cosmic string is, we need to rewind the clock to the universe's earliest, most violent instance. Physicists believe that as the hot, dense newborn cosmos expanded and cooled, it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. But this was a transition of the vacuum of space itself. In certain theories, these transitions might not have happened perfectly uniformly everywhere. Tiny defects could have been frozen into the very fabric of spacetime as it crystallized. Think of it like ice forming on a pond. As sheets of ice merge, tiny cracks and flaws can get trapped at the boundaries. Cosmic strings are one such flaw, but rather than a crack in ice, they are a flaw in the fundamental fields that define our reality. The properties of these objects are almost beyond comprehension. A cosmic string would be a one-dimensional topological defect, meaning it has length but essentially no width. It's thinner than a proton. Yet, despite its lack of girth, it would be phenomenally massive. A single centimeter of cosmic string could weigh more than a mountain range, concentrating an almost unimaginable amount of mass energy into an infinitesimally thin line. This extreme density warps spacetime around it in a very peculiar way. Instead of creating a spherical gravitational field like a planet or a star, a cosmic string's gravity would be highly asymmetric. Space around it would be flat, but if you were to travel in a complete circle around the string, you wouldn't end up where you started. You'd find yourself on a parallel path, as if space itself had been cut out and seamlessly stitched back together in a new configuration. This bizarre geometric effect is known as a conical singularity. So how could such a bizarre object possibly help us build a wormhole? The immense tension and density of a cosmic string generate a gravitational field so powerful it could literally punch a hole through the fabric of spacetime. One compelling theory suggests that if two cosmic strings were to move past each other at incredibly high speeds, their combined gravitational influence could warp spacetime so severely that a wormhole throat forms between them. It would be like two immensely heavy ships cutting through the ocean. The wake they leave behind could momentarily connect them in a tunnel of swirling water. In this case, the water is the fabric of the cosmos itself. An even more promising idea involves the geometry of the strings themselves. Some models propose that a wormhole could naturally form with each of its two mouths attached to a different cosmic string, or even that a single, looped cosmic string could act as the boundary of a wormhole mouth, holding it open like a wireframe defining the edge of a soap bubble. The incredible tension and negative pressure inherent in a cosmic string structure could, in theory, provide the same kind of repulsive gravitational effect we'd need from exotic matter. The string itself might act as the natural stabilizer, its intrinsic properties doing the job we had hoped to accomplish with manufactured exotic matter. The potential payoff is staggering. If a stable wormhole were tethered to cosmic strings, its size would be determined by the scale of the strings themselves. Unlike the microscopic quantum foam tunnels, these could be macroscopic, large enough for a planet, a solar system, or even a spacecraft to pass through. We would no longer be trying to inflate a subatomic bubble. We would be finding a naturally occurring interstellar tunnel system left over from creation and figuring out how to navigate it. This transforms the problem from one of impossible engineering to one of epic exploration. the challenge shifts from how do we build it to how do we find it and map it. Of course, this remains a highly speculative, though mathematically elegant idea. The existence of cosmic strings themselves is still theoretical, though they are a prediction of several well-regarded particle physics models. Astronomers have searched for their faint signatures, such as the unique gravitational lensing effects they would cause double images of a single galaxy or sudden jumps in the light from distant quasars, but conclusive evidence has yet to be found. Furthermore, even if they do exist, the energies and scales involved are so astronomically vast that manipulating them is far beyond any technology we can conceive of. Yet, the theory stands as a powerful testament to the creativity of cosmology, suggesting that the universe might have provided its own ready-made network of tunnels woven into the cosmos at the dawn of time, just waiting for a sufficiently advanced civilization to discover the map. So far, we've explored wormholes within the familiar 4 dimensions of spacetime, 3 of space and 1 of time. But what if our reality is just a tiny slice of a much grander, higher-dimensional cosmos? This brings us to one of the most ambitious frameworks in all of physics, string theory. At its heart, string theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. And for this mathematical elegance to work, the theory requires something extraordinary: extra dimensions of space, curled up into sizes so small we could never perceive them. It is within this lush, multidimensional landscape that wormholes may find a new, and perhaps more natural, home. The journey gets even more fascinating when we move to string theory's more comprehensive successor, known as M-theory. While string theory describes one-dimensional strings vibrating in 10 dimensions, M-theory unites several different string theories into a single, cohesive framework operating in 11 dimensions. This isn't just adding more spatial directions, it's proposing an entirely new geometric object, the membrane, or brane for short. Branes can have many dimensions themselves. A one-dimensional brane is a string, a two-dimensional brane is a membrane, and a three-dimensional brane is, well, that could be our entire universe. In this view, the three-dimensional space we inhabit might be one such brane, a flat island floating within a much larger, higher-dimensional bulk of space. This concept of branes completely revolutionizes how we might think about constructing a wormhole. In the classic Morris-Thorne model, a wormhole is a tunnel carved through the 4-dimensional spacetime of our universe. It's a daunting engineering project requiring exotic matter we may never find. But in the brane world scenario, a wormhole might not be a tunnel within our universe at all. Instead, it could be a higher dimensional bridge that connects our brane to another brane floating alongside us in the bulk. We wouldn't be bending the fabric of our own universe into a shortcut. We'd be simply stepping outside of it, taking a quick stroll through a higher dimension, and re-entering our reality at a different point, or even in a different universe entirely. This higher dimensional travel offers an elegant solution to one of the classic wormhole's biggest problems, the need for exotic matter. The gravitational forces acting within the full 11-dimensional bulk of M-theory operate under different rules. The severe warping of spacetime required to create a traversable throat might be achieved with the gravitational influence of higher dimensional objects like other branes, rather than relying on a mysterious substance we can't locate. The wormhole itself could be a fundamental feature of this higher dimensional geometry, a natural conduit between branes that is sustained by the larger laws of the bulk, making it far more stable and plausible than its 4-dimensional cousin. Imagine our universe as one page in a gigantic, multi-dimensional book. Each page is a separate brane, a complete universe with its own stars, galaxies, and physical laws. The pages are stacked together, but in the higher dimensional bulk, the space between the pages is just another dimension we can't access. A wormhole in this context would be like a tiny, thread-like tube that pierces through the pages, connecting them. A spacecraft could enter this tube from our page, travel through the higher dimensional gap between the pages, and exit out onto a completely different page, an entirely separate universe. The distances within our brain become almost irrelevant. The journey is about moving between realities, not just across the galaxy. The implications of this are staggering. It suggests that if wormholes do exist, they might not connect 2 points in our universe at all. They might be the sole means of travel between completely separate universes within a vast multiverse. This idea dovetails beautifully with the inflation theory of the Big Bang, which suggests our universe is just one bubble in a frothing cosmic foam of infinite universes. A higher dimensional wormhole could be the tunnel that connects these bubbles. This transforms the wormhole from a mere transportation device into a gateway of ultimate exploration, offering a potential method to test the multiverse hypothesis, one of the most profound ideas in modern cosmology. Of course, the challenge remains immense. The energy required to open a passage from our brain into the bulk, or to create a stable connection to another brain, is likely far beyond anything we can comprehend. Furthermore, the extra dimensions of string theory are curled up into a size known as the Planck length, which is about 20 orders of magnitude smaller than an atomic nucleus. Accessing them would require concentrating an astronomical amount of energy into a single point, a feat that may only be possible in the most extreme environments, like the immediate aftermath of the Big Bang or within the heart of a black hole. Yet, the sheer mathematical consistency of the idea offers a compelling vision that the ultimate shortcuts across the cosmos may not lie in navigating the universe we see, but in learning to voyage through the hidden dimensions we don't. While we often picture wormholes as incredible feats of future engineering, the universe might already be dotted with them, formed not by advanced civilizations but by the raw, untamed forces of nature itself. The conditions in the earliest moments of the cosmos were so extreme, so far beyond anything we can recreate, that they may have woven these tunnels directly into the fabric of spacetime. One of the most compelling ideas is that wormholes are primordial, born from the same violent quantum fluctuations that seeded all the galaxies and stars we see today. In the first fleeting instance after the Big Bang, the entire universe was compressed into an unimaginably hot, dense state, a seething cauldron where the very laws of physics were still settling into place. At this scale, quantum mechanics ruled supreme, and the fabric of reality was subject to wild, unpredictable fluctuations. These weren't tiny fluctuations like those in the quantum foam. These were titanic waves of energy warping the newborn spacetime itself. It's possible that some of these fluctuations were so powerful and had just the right characteristics to pinch off tiny regions of space, twisting them into a tunnel-like topology instead of a simple sphere. Think of it like blowing a bubble and having it somehow form a figure 8 shape instead of a perfect sphere, a rare but possible outcome given the right conditions. These nascent wormholes, if they formed, would have then been stretched to enormous sizes by the subsequent rapid expansion of the universe during the period of cosmic inflation. A microscopic tunnel forged in that first second could have been inflated to a macroscopic scale, potentially large enough to swallow a planet, all within a fraction of a heartbeat in cosmic time. The universe itself could be the ultimate wormhole factory, and these ancient relics might still be out there, drifting between the galaxies as hidden remnants of creation. Another natural formation theory points to the most cataclysmic events in the modern universe, the collisions of incredibly dense, massive objects. We know that when 2 black holes spiral inward and merge, they release stupendous amounts of energy in the form of gravitational waves, rippling the very fabric of spacetime. Some sophisticated computer models suggest that under just the right conditions, specific masses, spins, and collision angles, the incredible gravitational forces at play during such a merger could twist spacetime so severely that it momentarily forms a wormhole throat connecting the 2 objects before pinching off again. It wouldn't be a stable, traversable tunnel, but it provides a proof of concept that nature can, under immense strain, stitch together a shortcut through space. Furthermore, the collision of two neutron stars, the dense corpses of dead suns, could create a similar but even more exotic scenario. The incomprehensible density and the strange states of matter involved at their cores could provide a trigger, warping local spacetime into a tunnel as the two objects smash together. Perhaps the most dramatic natural formation theory involves the death throes of the largest stars. When a supermassive star many times heavier than our Sun reaches the end of its life and collapses, it typically forms a black hole. However, some theoretical models propose that for a star with just the right amount of rotation and magnetic field strength, the collapse might not result in a singularity, but could instead bounce, creating a temporary stable state known as a boson star or even a wormhole. In this scenario, the star wouldn't completely vanish behind an event horizon. For a brilliant, fleeting moment, it might open a gateway, a final flash of cosmic brilliance revealing a tunnel to elsewhere before the structure collapses. We might have already witnessed such an event in the form of certain unusual supernova or gamma-ray bursts whose energy signatures don't quite match our models for standard black hole formation. The universe's most spectacular deaths might be giving birth to its most incredible pathways. The search for these natural wormholes then becomes a grand challenge for astronomers. How do you find a tunnel that, by its very nature, might be invisible? The most promising method is through their gravitational effects, particularly gravitational lensing. A wormhole's mouth would have a tremendous gravitational pull, bending the light from stars and galaxies behind it. But unlike a black hole, which creates a single, telltale ring of distorted light, a wormhole's unique geometry might create a double image or even multiple anomalous images of the same background object. Astronomers could scan the skies for these strange lensing patterns, anomalies that can't be explained by the presence of a single spherical mass. Another signature could be the strange behavior of stars orbiting what appears to be a massive object at the center of a galaxy. If the object is a wormhole mouth and not a black hole, the star's orbit might exhibit subtle but detectable differences, a slight wobble or precession that betrays the unique structure hidden within. Finding such evidence would not just confirm the existence of wormholes, it would open a catalog of naturally occurring stargates, each one a potential destination for a future, incredibly adventurous civilization. But if nature hasn't provided us with a ready-made stargate, could we take matters into our own hands and build one? This leads us to one of the most ambitious and speculative ideas of all, the theory of artificial wormhole creation. For a civilization that has mastered the laws of physics, constructing a wormhole might not be a fantasy, but the ultimate engineering project, a megastructure on a cosmic scale. The first and most straightforward method, at least in theory, involves concentrating a truly astronomical amount of energy into a tiny region of space. Remember, mass and energy are equivalent. They both warp spacetime according to Einstein's famous equation. To create a significant warp, you need a staggering concentration of this energy. One of the most discussed concepts is the Krasnikov tube, a theoretical model for a warp drive that effectively creates a tunnel of altered spacetime. To build something like this, you would need to generate a ring of energy with a density greater than that of a neutron star and focus it with microscopic precision. The energy requirements are almost beyond calculation, potentially requiring more power than our entire Sun will output over its entire 10 billion-year lifespan, all channeled into a device perhaps no larger than a particle accelerator. This isn't just a power bill, it's about manipulating the fundamental energy fields of the vacuum itself, compelling spacetime to fold against its natural tendency and form a stable throat. Such a project would demand technologies that sound like magic to us today, perhaps involving the controlled collision of exotic particles or the creation of microscopic black holes to act as gravitational anchors for the forming wormhole. Beyond brute force energy, a more subtle approach might involve advanced quantum engineering. If the ER equals EPR conjecture is correct and wormholes are the geometric manifestation of quantum entanglement, then the key to building a wormhole might be to somehow geometrize entanglement. This would mean taking two particles that are already quantumly entangled and, through a process we can scarcely imagine, amplifying that connection, inflating it from a microscopic informational link into a macroscopic physical bridge. It would be like taking the spooky connection between two electrons and stretching it, widening it, until the empty space between them warps into a navigable tunnel. The technology for this wouldn't look like a traditional engine. It might resemble an immensely powerful quantum computer, programmed not to calculate, but to literally stitch the fabric of reality together by manipulating the underlying quantum code of spacetime. This process might also involve the deliberate creation and manipulation of exotic matter. While we've observed tiny amounts of negative energy in lab experiments like the Casimir effect, an advanced civilization might have discovered how to manufacture it in bulk. They could develop a kind of exotic matter reactor that doesn't produce power, but rather produces a stable output of this space-time repelling substance. This reactor would then be used to line the throat of the nascent wormhole as it forms, acting as a permanent support structure to counteract the gravitational forces trying to crush it shut. The entire construction might resemble less of a tunnel and more of a complex dynamic energy field, a carefully balanced dance of positive and negative energy densities that together hold the gateway open. The most visionary concept of all posits that a sufficiently advanced civilization wouldn't build a wormhole from scratch at all. Instead, they might mine one from the quantum foam. As we discussed, quantum theory suggests space is teeming with unimaginably tiny, transient wormholes blinking in and out of existence. A civilization that could manipulate reality at the Planck scale might have the technology to detect these fleeting events, capture one just as it forms, and then pump energy into it to inflate it to a usable size before it vanishes. They wouldn't be construction engineers so much as cosmic fishermen, casting a net into the seething quantum vacuum to catch a microscopic wormhole and then reeling it in, carefully nurturing it until it becomes large and stable enough for travel. This method would require an unimaginable degree of control over the quantum world, but it turns the entire universe into a supplier of raw materials, with every cubic centimeter of empty space holding the potential seeds for an interstellar highway. But all these grand visions of cosmic construction, whether harnessing primordial relics or manipulating quantum foam, run into the same monumental obstacle we encountered earlier: the crushing instability of the wormhole throat. The universe seems fundamentally opposed to keeping these space-time shortcuts open, bending its rules to snap them shut almost the instant they form. So if we ever hope to actually use one, we must find a way to fight back against nature itself, to build the ultimate support structure for our cosmic tunnel. This is the critical challenge of wormhole stabilization, and theorists have proposed several incredible, though wildly ambitious, methods to achieve it. The most famous solution, as we've touched on, involves a substance that defies the very nature of reality as we know it: exotic matter. Exotic matter isn't just rare or unusual, it possesses a property that turns physics on its head: negative energy density. In our everyday experience, all matter has positive energy density, which creates the attractive force of gravity we're all familiar with. Exotic matter would generate a gravitational repulsion, a kind of anti-gravity. Inside a wormhole, this repulsive force would be directed outward, pushing against the walls of the throat to counteract the immense gravitational pressure that is constantly trying to collapse it. Think of it like trying to keep an incredibly soggy paper straw from crumpling by lining its interior with a rigid, inflatable sleeve. The exotic matter acts as that rigid sleeve, providing the structural integrity the wormhole desperately lacks. The search for this miraculous material leads us back to the quantum world. We've already observed a microscopic version of this effect in the laboratory with the Casimir experiment. When two uncharged metal plates are placed extremely close together in a vacuum, they are pushed together by a faint force. This happens because the quantum fluctuations in the vacuum between the plates are restricted compared to the richer fluctuations outside, creating a minute pressure difference. The energy density between those plates is, mathematically speaking, negative. This proves that the concept isn't pure fantasy. It's a real, albeit tiny, quantum effect. The monumental challenge, however, is one of scale. Stabilizing a wormhole wide enough for a spacecraft would require not just a tiny amount, but a staggering quantity of this negative energy, potentially equivalent to the mass energy of Jupiter or more, all precisely concentrated to line the throat. We currently have no conceivable technology to generate, let alone contain, such a vast amount of exotic matter, making this approach a theoretical possibility but a practical nightmare. Another proposed method trades the mystery of exotic matter for the raw cosmic power of gravitational forces themselves. This is where the concept of cosmic strings could come into play. As we discussed, these are hypothetical, unimaginably dense filaments left over from the Big Bang, thinner than a proton yet heavier than a mountain range. Their extreme mass warps spacetime in a unique way, and some models suggest they could be used to mechanically stabilize a wormhole. One idea is that a wormhole mouth could be literally threaded onto a cosmic string, with the string's immense tension acting as a natural reinforcement for the throat, holding it open like a wire ring holds open the neck of a bag. The gravitational field of the string itself might provide the necessary repulsive force, eliminating the need for exotic matter altogether. The advantage of this cosmic string method is that it relies on a known gravitational phenomenon, however exotic the object may be. We wouldn't need to manufacture a universe's worth of bizarre matter. We would just need to find and harness a pre-existing cosmic string, a task that is itself astronomically difficult. The energy requirements, while still beyond our grasp, are tied to the natural properties of the string rather than a need for artificial generation. The feasibility then shifts from a question of energy production to one of cosmic scale engineering and navigation. Could we find a string? Could we move it or guide a forming wormhole onto it? These are the new, albeit still fantastical, questions this method raises. A third, even more speculative avenue explores the potential of pure geometry and higher dimensions to provide stability. In the framework of string theory and its extension, M-theory, our universe is a three-dimensional brane floating in a higher dimensional bulk. A wormhole in this context might not be a tunnel within our brain, but a bridge that passes through this bulk to connect to another point on our brain or even to another brain entirely. The laws of physics in the higher dimensional bulk could be different, allowing for a wormhole geometry that is inherently stable without needing exotic matter. The gravitational forces that cause collapse in 4 dimensions might be naturally counteracted when the full geometry of 11 dimensions is considered. In this view, stabilization isn't about adding a special substance. It's about finding or creating a wormhole whose path is through a region of spacetime where the rules are more forgiving. The energy requirement then becomes not about producing negative energy, but about the power needed to access or manipulate these higher dimensions, a challenge that is every bit as daunting but conceptually distinct from the others. When we compare these methods, we're really comparing different categories of impossibility. The exotic matter approach requires generating and controlling a substance we've only seen hints of on a scale that dwarfs our entire civilization's energy output. The cosmic string method depends on the existence of and our ability to manipulate hypothetical objects from the dawn of time. The higher dimensional solution demands a technology that can access and engineer the very fabric of reality at its most fundamental, hidden levels. Each path presents a unique set of astronomical energy requirements and technological hurdles, making it impossible to declare a clear winner in terms of feasibility. They all reside squarely in the realm of theoretical physics, beautiful mathematical solutions waiting for a future, perhaps infinitely more advanced, civilization to test their mettle against the universe's most stubborn laws. Assuming we could actually construct or find a stable wormhole, the next monumental challenge would be learning how to navigate it successfully. This isn't like plotting a course across the empty void of space. It would be more like piloting a vessel through the most violent and unpredictable cosmic rapid imaginable. The journey through a wormhole throat would be fraught with lethal hazards, and simply pointing your ship at one mouth and hoping to exit the other would be a sure path to catastrophe. Theorists believe that safe passage would require a sophisticated navigation system far beyond anything we possess today, one capable of making constant, real-time corrections to keep the vessel centered within the treacherous tunnel. The primary threat comes from the wormhole's own extreme gravity. Even a stabilized wormhole would generate immense tidal forces within its throat. These forces are the result of a difference in gravitational pull between one point and another. Imagine the difference between the gravity acting on your head and your feet if you were standing near a black hole. It would stretch you into a long, thin strand. Inside a wormhole, this spaghettification effect would be a constant danger. A navigation system would need to continuously adjust the ship's position to keep it within the precise center of the throat, the region where these tidal forces are theoretically at their weakest. Straying too close to the walls would subject the ship to gravitational gradients so severe they could tear its atomic structure apart. This would require sensors of unimaginable sensitivity, constantly mapping the gravitational topography of the tunnel ahead and making micro-corrections to the ship's trajectory, or perhaps even locally warping the space immediately around the vessel to create a safe bubble. Furthermore, the geometry inside the wormhole might not be a simple, straight tunnel. It could be chaotic, dynamic, and potentially even branching. Some theories suggest the interior could be a labyrinth of paths, with some routes leading to the desired exit and others terminating in dead ends or dangerous singularities. A navigation computer would need to solve this complex geometric puzzle in real time, identifying the correct path using some form of higher dimensional mapping that we can scarcely conceive of. It might rely on detecting subtle variances in quantum fields, gravitational wave echoes, or other exotic signatures to chart a safe course, essentially acting as a cosmic spelunker feeling its way through a dark and ever-shifting cave system. Beyond the physical navigation, there's the critical problem of aiming. How do you ensure the exit mouth is where you want it to be? The exit could be light years away, and even a tiny error in alignment at the entrance could result in missing the target solar system by trillions of miles. Precise navigation would demand a flawless understanding of the wormhole's connection to the external universe. This might involve creating a detailed gravitational map of the entire galaxy to accurately triangulate positions, or employing some form of quantum entanglement-based communication between the two mouths to provide an instant and unambiguous data link, ensuring the ship always knows exactly where it's going relative to the fixed stars outside the tunnel. Without this, a journey through a wormhole would be the ultimate leap into the unknown, with no guarantee of ever finding your way home. But what if the cosmic subway system had more than just two stations? Our journey into the theoretical now takes a turn into the truly labyrinthine with the idea of multi-mouth wormholes. So far, we've imagined a simple tunnel with an entrance and an exit, a direct line from point A to point B. Yet, the mathematics of general relativity doesn't necessarily limit us to such a straightforward setup. The equations allow for far more complex and bewildering structures. Wormholes with 3, 4, or even an infinite number of mouths, all connected through a central hub or a tangled web of throats, creating a sprawling network of shortcuts woven throughout the fabric of spacetime itself. Think of it like the difference between a simple bridge connecting two riverbanks and a massive, multi-level cloverleaf interchange on a highway. A single wormhole is the bridge. A multi-mouth system is the entire interchange, with on-ramps and off-ramps leading to dozens of different destinations. In this model, a traveler wouldn't just choose whether to go through the wormhole or not. They would arrive at a central nexus and have to choose which exit mouth leads to their desired time and location. Each mouth could be stationed in a different star system, a different galaxy, or even a different era in history, all accessible from a single, bewildering point of departure. The logistical possibilities of such a network are as staggering as they are complex. Imagine a future where humanity has established a mouth here in our solar system, connected to a central hub. From that hub, we could have established routes to a mouth orbiting a planet in the Proxima Centauri system, another in the heart of the Andromeda Galaxy, and a third positioned near Earth in the 25th century. A starship could depart from Jupiter, arrive at the hub, and then have its pick of destinations across both space and time. This wouldn't just be a means of travel, it would be the foundation of an entire interconnected civilization, a nexus of commerce, culture, and exploration on a scale we can barely fathom. However, this incredible connectivity comes with a host of dizzying paradoxes and potential dangers. The most obvious is the problem of causality, which becomes exponentially more tangled with every additional mouth added to the network. If one mouth leads to the past relative to another, the possibilities for paradoxes multiply. Information or matter could loop through the network, creating feedback loops with unpredictable and potentially universe-breaking consequences. The entire system would require unimaginably precise regulation to prevent, for example, a ship from exiting a mouth and accidentally colliding with its own past self, or a message being sent back in time to prevent the wormhole's own creation. Furthermore, the stability of such a complex structure is a profound question. In a simple two-mouth wormhole, exotic matter is needed to line the single throat and prevent collapse. In a multi-mouth system, the geometry at the central junction, where multiple throats converge, would be incredibly complex. The gravitational and topological stresses at this nexus point would be immense, potentially requiring new forms of stabilization we haven't even theorized yet. It's possible that the more mouths you add, the more exponentially difficult it becomes to keep the entire network from catastrophically imploding into a singularity. The civilization that could build and maintain such a structure wouldn't just be advanced, they would be masters of reality itself, capable of engineering spacetime with the same ease with which we build roads. This concept pushes the idea of a wormhole from a simple transportation device to the ultimate infrastructure. It suggests a universe that isn't just dotted with isolated shortcuts, but one that might be underpinned by a hidden, fundamental network of tunnels, a cosmic subway system built into the very architecture of creation. Finding evidence for such a network would revolutionize our understanding of the universe, hinting that the vast, empty distances between galaxies are an illusion, and that the cosmos is, at its heart, a deeply and intimately connected place. But if the immense energy required to stabilize a wormhole is the universe's way of telling us to keep out, there might be a key already hidden in plain sight, woven into the very expansion of the cosmos itself. This brings us to a theory that connects two of the greatest mysteries in physics: the enigmatic nature of wormholes and the baffling force known as dark energy. For decades, astronomers have known that the universe isn't just expanding. That expansion is accelerating, as if some invisible repulsive force is pushing all of space apart. The source of this push is called dark energy, and it makes up about 68% of all the energy in the universe, yet we have almost no idea what it actually is. Intriguingly, the properties of this mysterious energy might share a profound connection with the exotic matter we would need to prop open a wormhole. Recall that exotic matter is defined by its negative energy density and negative pressure, generating a gravitational repulsion that pushes spacetime outward. Now look at the observed effects of dark energy. It is causing the very fabric of the cosmos to stretch apart at an ever-increasing rate, an effect that can only be explained by a form of energy that also possesses a strong negative pressure. The parallel is striking. Could it be that dark energy is not some uniform field filling space, but is actually the collective effect of something far more intricate? One radical proposal suggests that what we perceive as the smooth, background energy of the vacuum is actually the result of an unfathomably vast number of microscopic wormholes, the very quantum foam tunnels John Wheeler imagined permeating every cubic centimeter of space. In this view, the vacuum of space isn't empty at all. It's a seething, fractal foam of Planck-scale wormholes constantly blinking in and out of existence. Each of these tiny tunnels, according to its own unique geometry, contributes a minute amount of negative energy. While one wormhole is far too small to have any detectable effect, the combined contribution of trillions upon trillions of them in every direction could add up to the pervasive, repulsive force we measure as dark energy. The accelerating expansion of the universe wouldn't be driven by a mysterious new field, but would instead be a gravitational side effect of the universe's fundamental, wormhole-riddled structure. The cosmos isn't expanding because of something in space. It's expanding because of what space itself is made of at the very smallest scales. This idea turns the challenge of wormhole stabilization on its head. Instead of us needing to produce astronomical quantities of exotic matter to build one large wormhole, the theory suggests that exotic matter is already everywhere, inherent to the fabric of reality. Our task would then shift from creation to extraction and concentration. A sufficiently advanced civilization might develop a technology that acts like a cosmic vacuum cleaner, somehow gathering and focusing this background froth of negative energy from a large volume of space into a single point, using it to inflate and stabilize a single macroscopic wormhole for travel. They wouldn't be creating anti-gravity from scratch. They'd be harvesting it from the quantum structure of the vacuum itself, tapping into the dark energy that already flows through everything. An alternative, even more mind-bending theory proposes that the connection works in the opposite direction, that macroscopic wormholes are not just consumers of exotic energy, but are actually the source of dark energy themselves. Imagine a universe where countless stable wormholes were formed in the first instance after the Big Bang, each one acting as a conduit between distant regions of spacetime. The intense negative pressure required to keep their throats open would have a gravitational effect on the space around them. As the universe expanded, the network of these primordial wormholes would stretch and evolve, and their collective repulsive gravity could manifest as the overall acceleration we observe. In this model, dark energy isn't a smooth force. It's the emergent property of a cosmic web of tunnels, a hidden architecture left over from the beginning of time that is only now, on cosmological timescales, making its presence known by pushing the universe apart. Testing these ideas is, of course, incredibly difficult. How do you detect a network of microscopic wormholes or distinguish their gravitational effect from that of a uniform dark energy field? Some cosmologists suggest looking for subtle anomalies in the precise rate of the universe's expansion over time, or in the cosmic microwave background radiation, the afterglow of the Big Bang. If dark energy is actually caused by a dynamic network of wormholes, its strength might not be perfectly constant, potentially showing tiny variations that our next generation of space telescopes could hope to detect. While these theories remain highly speculative, they represent a beautiful synthesis, daring to connect the largest-scale behavior of the entire cosmos with the smallest, most intricate structures that might form its very foundation. This brings us to a theory that attempts to solve one of physics' greatest puzzles by connecting two of its most bizarre phenomena. we're exploring the radical idea that the spooky, instantaneous connection of quantum entanglement might actually be facilitated by unimaginably tiny wormholes providing a physical bridge for information to travel. This concept seeks to unite the warring worlds of quantum mechanics and general relativity, suggesting that the fabric of spacetime itself might be stitched together by a hidden network of Planck-scale tunnels. To understand this, we need to revisit the sheer weirdness of quantum entanglement. When two particles become entangled, they share a single, unified quantum state. Measuring the property of one, its spin, for instance, instantly determines the property of the other, no matter if it's in the next room or on the other side of the observable universe. This instantaneous correlation seems to violate the cosmic speed limit set by the speed of light, a problem that so troubled Einstein he dismissed it as spooky action at a distance. For decades, physicists have accepted that this is just how the quantum world works, but the question of how the particles manage this feat has remained deeply mysterious. Is it a truly non-local connection, or could there be a hidden physical mechanism we haven't yet discovered? Some theorists propose that the mechanism might be hiding in plain sight within the equations of gravity. The idea is that what we perceive as quantum entanglement could actually be the result of these two particles being connected by a microscopic wormhole, an Einstein-Rosen bridge so small it operates at the Planck scale. In this view, the information about the particle's state isn't magically teleporting across space. It's taking a shortcut through a higher dimensional tunnel woven into the fabric of spacetime itself. The wormhole provides a direct physical conduit, making the connection local through a hidden geometric structure rather than a mysterious, spooky action. This theory finds its most powerful expression in the work of physicists like Juan Maldeisner and Leonard Susskind, who formulated the stunning equation ER equals EPR. This deceptively simple statement proposes that an Einstein-Rosen bridge, a wormhole, is physically equivalent to an Einstein-Podolsky-Rosen entangled pair. They are not just similar ideas, they are two different descriptions of the exact same underlying physical reality. According to this conjecture, every time we create a pair of entangled particles, we are also, perhaps without realizing it, creating a microscopic wormhole that connects them. The greater the degree of entanglement between two quantum systems, the shorter and more stable the wormhole bridging them becomes. The implications of this are breathtaking. It suggests that the strange, non-local quantum connections that underpin technologies like quantum computing and quantum teleportation are actually manifestations of a hidden gravitational geometry. The process of quantum teleportation, where the quantum state of one particle is transferred to another distant particle, might involve that information traveling through a fleeting wormhole that links them. This wouldn't allow for faster-than-light travel of matter or energy, but it could provide a physical mechanism for the instantaneous transfer of quantum information, resolving the spookiness by giving it a tangible, geometric explanation. This idea also offers a potential solution to the infamous black hole information paradox. If information falls into a black hole, is it lost forever, violating quantum mechanics? The wormhole entanglement connection suggests that black holes could be entangled with the radiation they emit, often called Hawking radiation. This entanglement would create a wormhole link between the black hole's interior and the outgoing radiation. Therefore, information that fell in isn't destroyed. It's meticulously preserved and encoded within the radiation, having passed through the wormhole connection. The information was never truly lost, it just took a hidden route out. If this theory is correct, it paints a picture of a universe that is fundamentally and deeply interconnected in a way we never imagined. Empty space wouldn't be empty at all. Instead, it would be a dynamic quantum foam, a seething network of Planck-scale wormholes that constantly form, connect, and vanish, entangling every particle with every other particle in a vast cosmic web. The solidity and separation we experience in our everyday lives would be an illusion, a classical approximation of a reality that is, at its most fundamental level, a labyrinth of tunnels weaving the cosmos into a single, inseparable whole. But if traversable wormholes are possible, even in theory, it forces us to ask a profound observational question. For decades, astronomers have been cataloging objects they confidently call black holes, from stellar mass remnants to the supermassive giants at the center of galaxies. But could some of these dark, incredibly massive objects actually be something else entirely? This leads us to a theory that challenges our basic assumptions, proposing that what we observe as black holes might in fact be the mouths of stable, massive wormholes. The challenge, then, is to find a way to tell them apart, to look for the subtle cosmic fingerprints that would betray a tunnel's presence over a one-way street to oblivion. The most promising place to search for this distinction is at the very edge of these objects, at the point of no return we call the event horizon. For a classical black hole, the event horizon is a one-way membrane. Light, matter, and information cross it and are lost to our universe forever, leaving behind only a few characteristics like mass, spin, and charge, an idea famously known as the no-hair theorem. A wormhole, however, would behave very differently. It wouldn't have a true event horizon in the same sense. While it would still have an immense gravitational pull, the throat might be passable. Instead of a point of infinite darkness, the center could be a gateway. This fundamental difference could manifest in ways we might just be able to detect with sophisticated instruments. One key signature would be the way these objects interact with matter. We believe that supermassive black holes, like Sagittarius, a star at the center of our Milky Way, are surrounded by a swirling, superheated disk of accreting matter. As this material spirals inward, it rubs together, creating friction and emitting intense radiation, particularly in X-rays, before it finally vanishes across the event horizon. If that object were a wormhole, the story might not end there. Some theoretical models suggest that matter and energy falling into a wormhole mouth could in part be ejected out of the other mouth. We might not see a complete disappearance. We might instead observe unusual and periodic bursts of energy or high-energy particles that seem to have no clear source, as if they were being spit out from somewhere else in the cosmos. The behavior of stars orbiting these central objects could also provide a crucial clue. Astronomers meticulously track the orbits of stars around Sagittarius, a star, using their paths to precisely measure the hidden mass they are circling. A wormhole mouth, while still incredibly massive, might have a slightly different gravitational field than a perfectly spherical black hole. Its unique topology could impart a faint but detectable wobble or precession to a star's orbit, a subtle deviation from the perfect ellipses predicted by a simple black hole model. It would be like detecting the presence of a hidden chamber in a pyramid not by seeing it, but by measuring the infinitesimal way its gravity tugs on a pendulum swinging in a room above. Perhaps the most dramatic way to distinguish them would be to look directly at the shadow of the object itself. In 2019, the Event Horizon Telescope collaboration made history by releasing the first ever image of the shadow of the supermassive black hole at the center of the galaxy M87. This dark circle, silhouetted against the glowing accretion disk, matched the predictions for a black hole's event horizon. However, some scientists have modeled what the shadow of a wormhole might look like. Due to the light-bending properties of its unique geometry, a wormhole's shadow could appear different. It might be smaller or lack the distinctive bright ring, or, most intriguingly, it might even show a faint, ghostly secondary glow at its very center, a hint of light coming from the other side of the tunnel, from a completely different region of space or time. Future generations of space-based telescopes with even higher resolution might be able to spot this telltale sign. This theory doesn't suggest that all black holes are wormholes. Most are almost certainly the classic gravitational traps described by general relativity. but it opens the door to the possibility that among the many dark objects we've catalogued, a few might be misidentified. One of them could be a gateway. The search for these cosmic imposters is not just an academic exercise. It's a direct test of the limits of our physical theories and a thrilling hunt for the most profound discovery imaginable. A ready-made stargate hidden in the dark heart of a galaxy, waiting for us to recognize it for what it truly is. This challenge brings us straight to one of the most elegant solutions proposed by theoretical physics, the Novikov self-consistency principle. Developed by Russian physicist Igor Novikov, this idea doesn't try to invent a complicated mechanism to prevent paradoxes. Instead, it makes a simple, profound statement about the nature of reality itself. The universe is a single, consistent, and immutable timeline. Any event that appears to cause a paradox simply cannot happen because it would violate this fundamental consistency. In this view, if you were to travel back in time through a wormhole, you wouldn't be entering a past you could alter. You would be stepping onto a stage where your role has already been written. Your actions in the past were always a part of that history. You might think you have free will to change things, but every choice you make would inevitably lead to the exact outcome that already occurred. If you travel back to prevent a famous assassination, for instance, you would inevitably fail. Your gun might jam, you might get caught in traffic, or you might even be the unknown cause of the event itself. Your presence in the past isn't a disruption. It's the completion of a loop that was always there, hidden in the details of history. The universe, in this model, possesses a kind of cosmic immune system that ensures all events, including time travel, are self-consistent and paradox-free. For many, this elegant solution feels restrictive, almost fatalistic. It raises the question, if we can't change anything, what is the point of time travel at all? This is where an alternative and perhaps more thrilling theory enters the stage, the idea of branching timelines or parallel universes. This concept suggests that every possible outcome of every event actually occurs, but in a separate, newly created reality. Within this framework, a wormhole might not be a tunnel to our own past, but a bridge to the past of a nearly identical parallel universe. When you step through and take an action, you aren't altering your own history. You are branching off a new timeline, creating a fresh universe where that new event becomes its immutable history. You could prevent that assassination, and the world you leave behind would continue unchanged, but you would now be trapped in a new reality where the consequences of that action play out. This resolves the grandfather paradox neatly because the person you interact with in the past isn't your actual grandfather from your original timeline, but a version of him from a parallel reality. Your actions have no causal effect on your own point of origin. This multiverse approach to paradox resolution is incredibly appealing because it offers both freedom and consequence. It allows for the exploration of what-if scenarios without the logical headache of erasing oneself from existence. However, it introduces a new set of profound questions about identity and connectivity. If you travel to a parallel past, are you truly traveling in time? Or are you just hopping between alternate realities that are at different points in their own chronological development? Furthermore, this theory suggests a universe of mind-boggling abundance, where an infinite number of new universes are constantly being spun off from every decision made by every time traveler. The energy requirements for such a process are incomprehensible, leading some physicists to doubt its feasibility. A more technological solution to the paradox problem involves the wormhole itself acting as a regulator. Some models propose that the immense energies and exotic physics at work within a stable wormhole throat might naturally prevent inconsistent events through a form of destructive feedback. The moment a paradox-threatening action is initiated, the conflicting timelines could create a gravitational or quantum instability that violently snaps the wormhole shut, severing the connection and protecting the integrity of the original timeline. In this scenario, the universe doesn't gently correct you, it slams the door in your face. The wormhole becomes its own guardian, a natural safety mechanism that only allows journeys and actions that are inherently self-consistent. Trying to force a paradox would be like trying to push two identical magnetic poles together. An invisible force pushes back with increasing strength until the connection is broken. Each of these theories offers a different philosophical perspective on the nature of time, free will, and reality. Novikov's principle presents a block universe where everything is predetermined and interconnected. The parallel worlds theory offers a dynamic, ever-branching multiverse of infinite possibilities. The destructive feedback model suggests a universe that actively protects its own causal structure. While we currently lack the means to test which, if any, of these models is correct, they provide the essential theoretical groundwork that makes wormhole time travel a subject of serious scientific inquiry rather than pure fantasy. They are the rules of the road for a journey we are not yet equipped to take, ensuring that if we ever do unlock the secrets of the wormhole, we will have at least some idea of the profound rules that govern the river of time itself. But even if we could solve the paradoxes and master the engineering, we would immediately face a challenge of literally cosmic proportions. Every single model for a traversable wormhole, from the simplest to the most complex, points to one undeniable and staggering requirement: an almost unimaginable amount of energy. We're not talking about the output of a few nuclear power plants. We're talking about energies that rival, and in some cases dwarf, the total output of entire stars over their multi-billion-year lifetimes. To grasp the scale, let's start with the most famous energy requirement in all of physics, the Planck energy. This isn't just a big number, it's the fundamental unit of energy in a quantum theory of gravity, the energy scale at which the fabric of spacetime itself is expected to become a chaotic quantum foam. The Planck energy is approximately 2 billion joules. Now, that might not sound like much. It's roughly the kinetic energy of a large passenger jet flying at cruising speed. The impossible part is the concentration. This energy must be focused into a volume of space defined by the Planck length, a scale a billion times smaller than a single proton. Concentrating that much energy into such a minuscule point is so far beyond our capabilities that it makes creating a star in a lab seem trivial by comparison. For creating a wormhole from scratch in the quantum foam, this is the energy barrier we're facing, and it is the ultimate expression of nature's reluctance to allow such shortcuts. When we look at more practical, albeit still theoretical, designs like the Morris-Thorne wormhole, the numbers become slightly more comprehensible but no less daunting. Stabilizing a wormhole with a 1-meter radius throat would require an amount of exotic matter with a negative energy density equivalent to the mass energy of Jupiter. Let's break that down. Jupiter's mass is about 1,000th that of our Sun. Using Einstein's famous equation, E equals mc squared, we can convert that mass into pure energy. The total energy output of our Sun over its entire 10 billion-year main sequence lifetime is estimated to be about 1.2 times 10 to the 44th joules. The negative energy required to hold open our modest 1-meter wormhole is a significant fraction of that astronomical figure. We would need to harness and manipulate the total energy output of a star for millions of years just to keep a doorway open that a person could walk through. The energy requirements scale dramatically with the size of the wormhole. If we wanted something truly grand, a throat large enough to allow a starship to pass through comfortably, say, a radius of 1 kilometer, the exotic matter needed could have a mass energy equivalent greater than that of the entire Milky Way galaxy, which contains over 100 billion stars. This isn't an engineering problem. It's a fundamental limit that seems to shout from the equations themselves that such structures are not meant to be. Some physicists have interpreted these colossal numbers not as a challenge to be overcome, but as nature's own form of cosmic censorship, a clear sign that traversable wormholes are permanently forbidden by the laws of physics, no matter how clever our future technology becomes. However, not all calculations are quite so pessimistic. Some more recent and speculative theories suggest there might be ways to drastically reduce the energy bill. One intriguing idea involves the dynamics of the wormhole itself. If a wormhole could be made to oscillate or vibrate at a specific resonance, the negative energy requirements might be reduced by many orders of magnitude. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's natural rhythm, a very small force can produce a very large result. Applying a tiny, carefully timed pulse of exotic energy to a resonating wormhole throat might be enough to keep it propped open, turning a project that requires the energy of a galaxy into one that might only need the energy of a star. Another potential shortcut lies in the nature of the exotic matter itself. Our calculations assume we need to manufacture and contain this material, but what if we could simply borrow it? Quantum mechanics allows for the temporary violation of energy conservation through the uncertainty principle, creating what are known as quantum interest conjectures. In this view, the exotic matter stabilizing a wormhole wouldn't be a permanent, paid-for quantity. It could be a quantum loan, a fluctuation of negative energy that is constantly being taken out and repaid, so the net energy over time remains zero. The stabilization wouldn't be a static structure, but a dynamic, shimmering effect, a delicate balancing act on the edge of reality that requires precision rather than raw power. While this is perhaps even more fantastical than the idea of manufacturing exotic matter, it illustrates that our first-pass energy calculations might be the crudest possible estimate, and that the universe in its infinite complexity might yet harbor loopholes for the truly ingenious. While the idea of cosmic-scale wormholes captures our imagination, some of the most compelling theories suggest the real magic might be happening on a scale so small we could never hope to see it directly. This brings us to the fascinating possibility that wormholes are not rare, colossal structures, but an utterly common feature of the quantum world, woven into the very fabric of reality at the tiniest of scales. These would be microscopic wormholes, and their existence could fundamentally reshape our understanding of the universe's most basic rules. The concept finds its roots in the mind of physicist John Wheeler and his vision of quantum foam. At the incredibly tiny Planck scale, a distance of about 1.6 times 10 to the negative 35 meters, the smooth, predictable geometry of spacetime is thought to break down completely. Instead of a calm, continuous fabric, the universe at this level becomes a seething, chaotic froth. In this turbulent environment, the uncertainty principle reigns supreme, allowing for wild fluctuations in energy and the very topology of space itself. It is within this frenetic foam that Wheeler proposed microscopic wormholes are constantly blinking into and out of existence. They form, connect two random points for a fleeting instant, and then vanish, all in a timescale so short it is essentially immeasurable. These tunnels are not built for spaceships. They are the geometric equivalent of virtual particles, ephemeral features of the vacuum that borrow energy from nothingness only to return it almost immediately. The potential stability of these objects is a subject of intense theoretical interest. While they are transient by nature, the strange rules of quantum mechanics might allow them to persist in a probabilistic sense. They wouldn't be stable in the way a planet is stable, but they could have a well-defined probability of existing at any given moment, contributing to the overall quantum texture of spacetime. Their stability wouldn't be mechanical but statistical, governed by the same quantum laws that allow a particle to be in two places at once. At this scale, the immense tidal forces that would tear apart a macroscopic wormhole might be mitigated or even rendered irrelevant by quantum effects, allowing these tiny tunnels to form and dissolve without the catastrophic gravitational consequences their larger cousins would face. This leads to a profound question. If spacetime is indeed riddled with these microscopic tunnels, what influence could they have on the world we actually observe? One revolutionary idea is that they could provide a physical mechanism for one of the strangest phenomena in all of physics, quantum entanglement. When two particles become entangled, their properties are linked instantaneously across any distance, a connection Einstein famously called spooky action at a distance. But what if that spooky action isn't action at all? What if it's simply a case of the particles being connected by a microscopic wormhole, a Planck-scale Einstein-Rosen bridge? In this view, the information about a particle's state isn't magically teleporting. It's taking a hidden shortcut through a tunnel in the quantum foam. The entanglement is not a mysterious force, but a geometric feature of spacetime itself, making the connection local through a hidden dimension. The implications for particle physics are staggering. The fundamental forces that govern how particles interact could be mediated or influenced by this underlying frothy structure. The path an electron takes might be subtly affected by the presence of these fleeting wormholes, potentially offering new explanations for certain quantum probabilities and behaviors that currently seem random. It could mean that the vacuum of space is not empty but is instead a dynamic, living medium, buzzing with microscopic connectivity. Every cubic centimeter of nothingness might be a vibrant network of ephemeral tunnels, constantly stitching the universe together at its most fundamental level. This isn't just a new particle or force, it's a radical reimagining of the stage upon which the particles and forces perform, suggesting that the quantum weirdness we struggle to explain is simply the visible effect of a hidden geometric reality teeming with microscopic wormholes. Yet the multiverse concept isn't confined to string theory's higher dimensions. It also emerges from one of cosmology's most successful models, the theory of eternal inflation. This idea suggests that the Big Bang wasn't a one-time event, but rather a localized occurrence within a much larger, eternally expanding meta-universe. In this vast, frothing sea of spacetime, quantum fluctuations can cause certain regions to stop inflating rapidly and instead bubble out, each one cooling down to form its own distinct universe with potentially unique physical laws and constants. Our entire observable cosmos, with its hundreds of billions of galaxies, might just be one such bubble in an infinite, ever-growing cosmic foam. The breathtaking implication is that wormholes could be the natural tunnels connecting these bubble universes. Instead of being shortcuts within our own cosmos, they might be the only structures capable of bridging the unimaginable gaps between these completely separate realities, each one a self-contained universe with its own history and physics. A traversable wormhole in this context would be the ultimate gateway, offering a passage from our bubble to another, potentially allowing travel to a universe where the laws of nature are fundamentally different, where gravity is stronger, the speed of light is slower, or even where time itself flows in an entirely unfamiliar way. This transforms the wormhole from a mere transportation device into a tool for the most profound exploration imaginable. For scientists, a multiverse-connected wormhole would be the ultimate laboratory. By traveling to a universe with slightly different constants, we could finally test why our own universe seems so finely tuned for life. Is it simply a cosmic accident, or is there a deeper reason? We could observe universal laws operating under different conditions, providing insights into physics that are impossible to gain from studying our single universe in isolation. The philosophical ramifications are equally staggering. It suggests that our reality is not the entirety of existence, but merely one page in an infinite cosmic library. The existence of such a network of tunnels would imply a cosmos that is not just vast in space, but vast in possibility, with every conceivable variation of physical law playing out in some universe somewhere. The wormhole becomes the ultimate symbol of connectivity, not just between stars but between entire realities, hinting that the cosmos is far more interconnected, rich, and strange than we could ever have dreamed. Even with the most advanced stabilization methods, every wormhole would face the constant and looming threat of collapse. The universe appears fundamentally predisposed to snap these space-time shortcuts shut, and understanding the various mechanisms that could trigger such a catastrophic failure is crucial. One of the most persistent dangers comes from the quantum world itself. The vacuum of space is not empty. It is a seething sea of virtual particles that constantly pop in and out of existence. When this quantum foam interacts with the intensely warped geometry of a wormhole throat, it can create instabilities. Fluctuations in energy could disrupt the delicate balance between the attractive gravity of normal matter and the repulsive effect of the exotic matter lining the throat. If this balance is even momentarily disturbed, it could initiate a cascading failure. The throat would begin to pinch, and the negative energy supporting it might not be able to respond quickly enough to counteract the collapse, leading to a rapid and irreversible closure. The very act of travel could be the cause of a wormhole's demise. Most theoretical models assume a wormhole is stable when empty, but the introduction of matter and energy, like a spaceship, could be a destabilizing event. As an object passes through the throat, its positive mass and energy would gravitationally attract the walls of the tunnel. Think of it like walking through a narrow, wet paper towel tube. Your presence makes it more likely to crumple. In a wormhole, this attraction adds to the stress already trying to crush the throat shut. For a perfectly engineered wormhole, the exotic matter might compensate for this additional load, but any imperfection in the system or an object more massive than the design specifications could overload the supports. The wormhole might tolerate the passage of a small probe but catastrophically collapse when a starship attempts to cross, sealing the tunnel and dooming the vessel. The fate of anything caught inside during a collapse is a subject of intense and grim speculation. As the throat pinches shut, the gravitational tidal forces would become infinite at the point of closure. Any matter present would be caught in a gravitational vice, crushed out of existence or propelled toward a terrifyingly uncertain destiny. One possibility is that the collapsing wormhole forms a black hole singularity at the moment of closure. Anything inside would be irrevocably lost, added to the mass of the newly formed singularity, its information potentially lost forever to our universe. Another, more speculative theory suggests that the collapsing wormhole might not simply vanish but could act as a gateway one final time, ejecting its contents into a random point in spacetime just before the connection is permanently severed. This would be a violent and unpredictable event, like being thrown from a catapult made of spacetime itself, with no control over the destination or time period of arrival. Perhaps the most dramatic collapse trigger would be a paradox. If a wormhole is being used for time travel and an action is taken that threatens to create a causal loop, like the classic grandfather paradox, some physicists believe the universe would enforce consistency through a radical correction. The immense conflicting energies of the paradox could manifest as a destructive feedback loop within the wormhole's structure. Quantum fields would become unstable, overloading the exotic matter supports and causing the entire geometry to break down. In this scenario, the wormhole doesn't just collapse, it might unravel, violently severing the connection to prevent a logical inconsistency from infecting the broader timeline. The collapse would be the universe's ultimate safety mechanism, a fail-safe that ensures the laws of cause and effect are never truly broken, even at the cost of destroying the most incredible invention imaginable. But if these incredible structures are out there, how would we ever find them? The challenge of spotting a wormhole is immense because to a distant observer, it could easily masquerade as something far more common and just as dark, a black hole. Both would appear as regions of immense gravity, bending light and trapping anything that comes too close. The key to telling them apart lies in searching for the subtle, telltale anomalies, the tiny cracks in the disguise that betray the presence of a tunnel instead of a bottomless pit. Astronomers and physicists have developed several ingenious methods to hunt for these cosmic fingerprints. turning the problem of detection into a fascinating exercise in cosmic forensics. One of the most promising techniques involves the precise study of gravity's effect on light, a phenomenon known as gravitational lensing. We know that any massive object, whether a star, a black hole, or a wormhole, warps the spacetime around it, acting like a lens to bend and distort the light from objects behind it. A black hole typically creates a specific pattern, a dark circular shadow surrounded by a bright, distorted ring of light from the background source. However, the unique geometry of a wormhole could create a distinctly different signature. Because a wormhole throat has a different shape and lacks a true event horizon, some models suggest its gravitational lens might produce multiple images of the same background object, or an anomalous pattern that doesn't match the clean, predictable distortion of a simple spherical mass. Most intriguingly, if a wormhole is truly a tunnel, there's a chance that a tiny amount of light could pass all the way through from the other side. This could create a faint secondary glow at the very center of the lensed image, a ghostly beacon shining from a universe or a time far away, a hint that you're not looking at an endpoint but a gateway. Beyond just bending light, a wormhole might reveal itself through the strange behavior of matter in its vicinity. Consider the supermassive object at the heart of our own galaxy, Sagittarius, a star. We observe stars like S2 whipping around it in incredibly fast, tight orbits, their paths allowing us to precisely calculate the hidden mass they're circling. If that object were a wormhole instead of a black hole, its gravitational field might have subtle imperfections. While a black hole's gravity is perfectly described by its mass, spin, and charge, a wormhole's more complex topology could impart a faint wobble or precession to a star's orbit, a slight deviation from the perfect ellipse predicted for a pure black hole. It would be an incredibly subtle effect, but next-generation telescopes and decades of precise monitoring might just be able to spot this gravitational whisper, a signature that the object they're orbiting isn't a simple singularity. The most dramatic evidence might come from the violent demise of a star that ventures too close. If a star were pulled apart by the tidal forces of a black hole, its material would form a hot accretion disk, spiral inward, and vanish, producing a specific flare of radiation before going dark. But if it were consumed by a wormhole, the story might have a different ending. Some theoretical models suggest that a portion of the stellar material could be ejected out of the wormhole's other mouth. Astronomers might observe the initial flare of the tidal disruption event, followed by a second, unexpected burst of energy appearing somewhere else in the sky millions of years later with a matching energy signature. It would be as if the star was being shredded here and then reassembled over there, a cosmic magic trick with a wormhole as the secret trapdoor. Finding such a correlated pair of events across vast stretches of space and time would be incredibly challenging, but it would also be one of the most compelling pieces of evidence imaginable for a traversable tunnel through spacetime. The hunt is already underway. Scientists are meticulously analyzing data from gravitational wave observatories, radio telescope arrays, and space-based telescopes, looking for any anomaly that defies conventional explanation. They are developing sophisticated computer models to simulate what a wormhole would look like under every conceivable circumstance. They are not just waiting for an accident discovery. They are actively defining the search parameters for the most elusive object in theoretical physics. The discovery wouldn't just be a headline, it would be a paradigm shift, proving that our universe is not just a collection of isolated points, but a deeply interconnected network, and that the greatest adventures might not be in crossing the vast emptiness between stars, but in finding the doorways that have been there all along. However, while traversing a rotating wormhole presents a thrilling possibility, it introduces a new and even more bewildering set of challenges for any would-be chrononaut. The intense frame dragging within the throat creates a chaotic and disorienting environment. Space itself is being twisted around the axis of rotation, meaning that simply pointing your ship at the exit might not be enough. Your trajectory would be constantly wrung through this cosmic ringer, requiring a navigation system capable of making constant, real-time corrections to account for the swirling flow of spacetime, fighting against the current to stay on a path that actually leads to the exit rather than being spun off into the unknown. Furthermore, the very center of a rotating wormhole might not contain a simple, benign throat. Some mathematical solutions suggest the presence of a Cauchy horizon, a boundary beyond which predictability breaks down completely and the laws of physics as we know them may cease to apply. Crossing this threshold could be a point of no return, plunging a traveler into a region of infinite tidal forces or a causality-violating nightmare where cause and effect become utterly meaningless. The Care wormhole, for all its theoretical elegance and potential freedom from exotic matter, might be the ultimate cosmic roller coaster, a ride that is as terrifying as it is tantalizing, offering a shortcut through the universe at the potential cost of sanity, safety, and the very predictability of reality itself. But to truly understand how the universe might keep a wormhole stable at its most fundamental level, we must venture beyond the classical physics of Einstein and into the strange, probabilistic world of quantum gravity. This is the final frontier of theoretical physics, a quest to unite the smooth, geometric reality of general relativity with the fuzzy, uncertain domain of quantum mechanics. And within this quest, various competing approaches offer radically different visions for the fate of wormholes, each one proposing a unique solution to the problems that plague them in classical theory. The central question is profound. Does quantum gravity smooth out the singularities and provide a natural stability that classical physics forbids, or does it erect even greater barriers to these cosmic shortcuts? One of the most prominent contenders is loop quantum gravity. Unlike string theory, which proposes extra dimensions, LQG attempts to quantize spacetime itself, suggesting that space is not smooth and continuous but is instead composed of tiny, discrete loops woven into a finite fabric. This granular structure has a startling implication for the centers of black holes and, by extension, wormholes. In classical general relativity, matter falling into a black hole is crushed into an infinitely dense point of no return, the singularity. But LQG predicts that at the extreme densities where quantum gravity takes over, this collapse is reversed by a powerful repulsive force, causing a quantum bounce. In this model, what we perceive as a black hole could actually be the entrance to a wormhole, and the singularity is replaced by a tunnel that leads to a white hole erupting into another region of spacetime. This provides a natural, quantum mechanical mechanism for wormhole formation that requires no exotic matter. The repulsive quantum geometry itself holds the tunnel open. The instability is solved not by adding a mysterious substance, but by rewriting the rules of physics at the Planck scale, turning catastrophic endpoints into gateways. Another fascinating approach comes from the theory of causal sets. This framework proposes that spacetime is fundamentally discrete, composed of a vast number of individual atoms of spacetime. The key idea is that these atoms are partially ordered, meaning they have a defined sequence of cause and effect, hence the name causal sets. In this view, a wormhole would represent a profound anomaly in this causal ordering. It would be a region where the neat sequence of cause and effect breaks down, creating a closed loop in the network. Intriguingly, the discrete nature of causal sets might naturally suppress the formation of such loops. The theory could inherently contain a built-in chronology protection mechanism, where the probability of a wormhole forming that allows time travel becomes vanishingly small. Rather than resolving the instability, causal sets might show us that the universe's fundamental building blocks are wired to prevent paradoxes from ever occurring, making traversable wormholes not just unstable but statistically impossible. Then we have the approach of asymptotically safe gravity. This complex theory suggests that gravity might be a valid quantum theory without requiring new dimensions or discrete spacetime, but by having a special property called asymptotic safety. This means that at extremely high energies, like those found in a wormhole throat, the strength of gravity approaches a fixed finite value instead of diverging to infinity. If this is true, it could smooth out the violent quantum fluctuations that would otherwise destabilize a wormhole. The terrifying singularities predicted by classical physics might simply melt away under the influence of this quantum smoothing, allowing for a stable wormhole geometry without the need for impossible amounts of exotic matter. The throat could be held open by the renormalized strength of gravity itself, a subtle quantum effect that makes the entire structure viable. Each of these approaches offers a different answer, painting a spectrum of possibilities for the quantum future of wormholes. Loop quantum gravity gives us a universe where wormholes are natural outcomes of stellar collapse. Causal sets suggest a cosmos where they are forbidden by its very atomic structure. Asymptotically safe gravity provides a middle path where quantum effects gently modify gravity to make wormholes possible. What becomes clear is that the classical problems of instability and exotic matter are not the final word. They are simply the questions we must ask before we have a complete theory of quantum gravity. The ultimate fate of the wormhole, whether it remains a tantalizing mathematical fantasy or is revealed as a genuine feature of our quantum universe, depends entirely on which of these competing visions, if any, truly describes the fabric of reality at its very smallest scales. But if we could actually build or discover a stable wormhole, the potential applications would extend far beyond simply moving physical objects from one point to another. One of the most transformative possibilities is the chance to revolutionize the very way we communicate across the cosmos, breaking the ultimate speed limit imposed by the universe itself. This brings us to the fascinating realm of wormhole communication theories, which explore whether these spacetime tunnels could be used to send information faster than light, and even through time itself, challenging our most fundamental notions of cause and effect. At its core, the dream of faster-than-light communication is about overcoming the tyranny of distance imposed by Einstein's special relativity. The speed of light, while incredibly fast, is still tortuously slow on an interstellar scale. A simple radio signal sent to a potential civilization orbiting Proxima Centauri would take over 4 years just for a one-way trip, and a conversation would span decades. This makes meaningful dialogue across the galaxy practically impossible. A traversable wormhole, however, offers a breathtaking solution. If we could place one mouth of a wormhole here on Earth and the other on a spaceship or a colony in a distant star system, we could potentially communicate through it instantly. A signal beamed into the local mouth would exit the distant mouth light years away in virtually no time, as the tunnel bypasses the external space between the 2 points. This wouldn't be breaking the speed of light within either region of space. It would be cleverly circumventing the long journey altogether, creating a network of real-time communication links that could bind a galactic civilization together. The implications of such a system are staggering to contemplate. It would allow for the instantaneous relay of scientific data from the edge of explored space, letting researchers on Earth observe the conditions around a distant exoplanet in real time. It could enable a form of interstellar telepresence where we could operate machinery or conduct experiments on another world without the debilitating light speed delay. Most profoundly, it would shatter the isolation of spacefaring communities. Families separated by light years could speak to each other as if they were in the next room, preserving the cultural and social bonds essential for a cohesive interstellar society. This wormhole network would become the ultimate internet, a web of connections weaving across the galaxy, turning a collection of isolated outposts into a truly united community. Yet, this incredible power comes with a profound and dangerous caveat. If a wormhole can be used for communication, and if that wormhole has been manipulated for time travel as we discussed earlier, then it could also become a device for sending messages into the past. Imagine we have our two-mouth wormhole, with one mouth having been on a high-speed journey, creating a fixed time difference between them. If the mouth on Earth is 5 years in the future of the other mouth, then a message sent into the Earth mouth would instantly arrive at the other mouth 5 years in the past. You could send a warning about a future disaster, a set of lottery numbers, or even instructions to your past self. This is where the theoretical fantasy crashes headlong into the hard wall of logical paradox. The most famous of these is the equivalent of the grandfather paradox for information, the bilking paradox. Imagine you receive a message through the wormhole from your future self that simply says, "Do not send the message." If you obey the message and never send it, then how did you receive it? The information has no origin. It exists in a closed loop, defying any logical explanation for its creation. This is more than just a philosophical puzzle. It suggests a fundamental inconsistency that physics seems to abhor. Sending information back in time doesn't just allow for the possibility of changing the past. It creates situations that are logically impossible, where effects can precede their own causes in a way that unravels the very fabric of rational reality. Physicists have proposed several ways the universe might prevent such paradoxes from occurring. One is the Novikov self-consistency principle, which we touched on earlier. Applied to communication, it would mean that any message you try to send back in time would be inevitably garbled, altered, or otherwise prevented from creating a paradox. You might intend to send a clear warning, but quantum noise or static would interfere, ensuring the message that arrives is useless or even counterproductive, always resulting in the timeline that already happened. The universe, in this view, possesses a kind of cosmic censorship that enforces a single, consistent history, making paradoxes physically impossible through subtle, corrective feedback. An alternative, and perhaps more terrifying, resolution is that the act of sending a paradoxical message would trigger the immediate and catastrophic collapse of the wormhole. The conflicting timelines would create an unstable feedback loop of energy within the throat, overloading the exotic matter supports and causing the entire structure to violently pinch off. In this scenario, the universe doesn't gently correct you. It slams the door shut, permanently severing the connection to protect the integrity of causality. The wormhole acts as its own fuse, blowing out to prevent a short circuit in time. This suggests that while faster-than-light communication within the same time period might be stable, any attempt to use the system for chronological messaging would be a risky, one-shot experiment with a high probability of destroying the most valuable asset imaginable. These theories of wormhole communication force us to confront the deepest questions about the nature of information, causality, and reality itself. They suggest that the universe might have strict rules governing not just what we can do, but what we can know and when we can know it. The ability to send a message faster than light is one thing, but the ability to send that message into the past may be a power the cosmos reserves for itself, forever placing it just beyond our reach to preserve the logical order that makes science and indeed existence possible. But before we pack our bags for a journey through a cosmic shortcut, we have to ask a profoundly human question. What would such a trip actually do to us? We've explored the physics of keeping the tunnel open, but what about the biology of the traveler? This leads us to a critical and often overlooked area of speculation: the potential biological effects of wormhole travel. Moving from the realm of pure physics to the messy, complex world of living organisms introduces a whole new universe of challenges and terrifying possibilities, from the crushing forces of extreme acceleration to the utterly unknown realm of quantum biology. Let's start with the most immediate and visceral threat: the physiological impact of the journey itself. Even with a perfectly stabilized Morris-Thorne wormhole, the act of entering, traversing, and exiting the throat would subject the human body to forces beyond anything we experience on Earth. The primary danger is tidal gravity. Imagine the difference in gravitational pull between your head and your feet if you were standing near a black hole. it would stretch you into a long, thin strand in a process gruesomely nicknamed spaghettification. A wormhole's throat, by its very nature, is a region of immense and complex gravity. While the design aims to minimize these tidal forces at the very center of the throat, even a slight deviation from that perfect path could be fatal. The gravitational gradient could literally pull a body apart, separating bone from muscle and cells from each other. A spacecraft would need to have an incredibly sophisticated navigation and stabilization system, not just to guide the ship, but to create a localized, safe zone of minimal tidal force around it, effectively ironing out the wrinkles in spacetime immediately surrounding the vessel to protect its fragile biological cargo. Beyond the brute force of gravity, there's the problem of acceleration and g-forces. To reach a wormhole mouth that's been positioned for a journey, perhaps by being moved at a significant fraction of light speed, a ship would need to accelerate and decelerate dramatically. The human body can only tolerate so many g-forces before losing consciousness or suffering catastrophic internal injury. Fighter pilots wearing special suits can handle up to about 9 Gs for short periods. The accelerations required for interstellar travel would likely far exceed this, requiring either a very slow, gradual journey to the wormhole entrance defeating the purpose of a shortcut, or a revolutionary technology that could somehow negate the effects of inertia inside the ship, perhaps by manipulating gravity itself within the crew cabin to create a constant, Earth-like environment. Regardless of the ship's external motion, then we venture into the truly unknown, the potential effects of the wormhole environment on the fundamental processes of life. The interior of a wormhole would be a place where the classical laws of physics blur into the quantum realm. This could have bizarre and unpredictable consequences for biological systems. Our DNA, our neural pathways, even the precise electrochemical balances that keep our cells alive, all operate on a molecular scale where quantum effects are usually negligible. But exposed to the extreme conditions within a wormhole, intense fields, potential quantum fluctuations, and who knows what else, these delicate processes could be disrupted. Could the strange geometry of the tunnel affect the quantum entanglement that some scientists believe plays a role in enzyme efficiency or even in consciousness itself? Might the journey cause irreversible mutations at a genetic level, or disrupt the fragile quantum coherence that is theorized to be involved in processes like photosynthesis and bird navigation? We are entering a complete frontier of science here called quantum biology, and placing a human being into such an environment would be the ultimate experiment with an unknown outcome. This leads to the most chilling possibility of all, temporal biological dissonance. If the wormhole is being used for time travel, the traveler's body would be out of sync with the universal flow of time they enter. Every process in our body, from cellular division to neural activity, is tuned to the rhythm of time as we experience it. What would happen to a body that suddenly found itself decades or centuries in the past or future relative to its own internal clock? Would our cells age rapidly to catch up to the new time frame? Or would they stubbornly hold onto their original rhythm, causing a profound and debilitating dissonance between the traveler and the new environment? The psychological impact of such a shift is one thing, but the physiological impact could be equally severe, disrupting circadian rhythms, metabolic rates, and hormonal cycles in ways we cannot possibly predict. A journey through a wormhole might not just be a trip through space, but a voyage into a biological unknown, challenging the very definition of what it means to be a living, functioning organism in a consistent flow of time. But perhaps the most profound connection lies in the reverse idea, that consciousness doesn't just navigate wormholes but might actively participate in creating them. Some theorists, drawing from the controversial field of quantum brain dynamics, propose that the incredible electrochemical activity within our own neural networks could generate conditions ripe for microscopic spacetime tunneling. Every thought, every firing synapse involves the movement of ions and the fluctuation of energies at a quantum scale. In the unfathomably dense and active environment of the brain, these fluctuations could, in theory, be significant enough to momentarily warp local spacetime, creating fleeting, Planck-scale wormholes that connect different neural regions. These microscopic tunnels could facilitate the near-instantaneous integration of information across distant parts of the brain, providing a physical mechanism for the binding problem of consciousness, the mystery of how our subjective experience feels unified and coherent, rather than like a collection of separate signals. In this speculative view, the magic of conscious thought isn't just a biochemical process. It might be a geometric one, with our minds constantly weaving and unweaving the very fabric of reality at a microscopic level to create a seamless experience of self. This leads to an even more radical proposal, the idea of a conscious universe. If the human brain can generate these effects, then what of a cosmic mind? Some interpretations of panpsychism, the philosophy that consciousness is a fundamental and ubiquitous feature of the universe, suggest that a universal consciousness could be entangled with the fabric of spacetime itself, its thoughts and perceptions manifesting as the large-scale structures we observe, including wormholes. In this view, a traversable wormhole isn't just a tunnel through space. It could be a literal thought in the mind of the cosmos, a connection formed by a universal will. This blends metaphysics with theoretical physics in a way that is currently untestable, but it offers a breathtakingly poetic vision of reality, that the universe is not a cold, empty void, but a living, thinking entity, and that the shortcuts through its expanse are the pathways of its own boundless imagination. While firmly in the realm of speculation, these ideas challenge us to expand our definition of what is possible, suggesting that the final frontier of wormhole exploration might not be out among the stars, but deep within the mysterious connection between our own minds and the universe that gave them birth. While the equations of physics paint a picture of delicate, unstable structures requiring impossible energies, the silver screen offers a far more glamorous and accessible vision. Stepping through a wormhole in film is often as simple as flying a spaceship into a shimmering, beautiful vortex, emerging moments later in a distant part of the galaxy without so much as a bumpy ride. This dramatic simplification is, of course, a necessity of storytelling. The intricate dance of exotic matter and quantum foam doesn't exactly make for a thrilling 2-hour visual spectacle. Yet, nestled within these Hollywood fantasies, there are surprising grains of scientific truth that filmmakers sometimes, either by accident or through careful consultation, manage to get remarkably right. One of the most common and accurate tropes is the connection between wormholes and extreme gravity. In the cinematic epic Interstellar, the crew visits a planet orbiting Gargantua, a supermassive black hole, and the time dilation they experience is a direct and brilliantly visualized consequence of general relativity. While the film takes creative license with the interior of the black hole itself, its portrayal of the wormhole, a shimmering, spherical portal, is grounded in the legitimate Morris-Thorne model. The visual effect artists even worked with physicist Kip Thorne to ensure the gravitational lensing around the wormhole, which warps the light from the distant galaxy on the other side, was rendered with scientific accuracy. This commitment resulted in genuinely educational imagery, showing audiences what a traversable wormhole might actually look like to an approaching astronaut. However, for every moment of accuracy, there are a dozen dramatic liberties. The sheer stability and user-friendliness of movie wormholes are their biggest departure from reality. Films like Stargate and Contact present wormholes as stable, long-lasting gateways that can be opened with a specific technology or frequency. In reality, keeping a wormhole throat from collapsing requires either exotic matter we can't produce or cosmic strings we can't find. The serene, calm journey through the tunnel is another fantastical element. A real traversal would likely be a terrifying ordeal of crushing tidal forces, chaotic spacetime geometry, and the ever-present threat of a catastrophic collapse, a far cry from the smooth, star-filled tunnel shown in 2001, A Space Odyssey, or the psychedelic tunnel of contact. Perhaps the most egregious Hollywood invention is the idea of wormholes as precise, point-to-point transportation systems that can be dialed like a telephone. In Stargate, an ancient device allows characters to connect to a specific wormhole leading to a predetermined planet across the universe. This concept of a targeted, addressable network is pure fiction. According to our best theories, manipulating the exit point of a wormhole would require controlling the geometry of the entire universe on a fundamental level, or at the very least, moving one of the mouths at relativistic speeds, a process that would take centuries and unimaginable energy. The wormholes of science are not a subway map. They are more like a single, fragile bridge that, if it existed, would have two fixed-in points determined by the conditions of its creation. Yet, even with these exaggerations, the role of pop culture is invaluable. It serves as a gateway itself, sparking curiosity and wonder in millions of people who might never pick up a textbook on general relativity. The dramatic, visually stunning portrayals of wormholes in movies and TV shows ask the all-important question: what if they inspire a new generation of scientists, engineers, and dreamers to explore the real physics behind the fantasy? While we may never pilot a starship through a serene, blue-hued vortex, the fictional depiction fuels our very real desire to understand the universe's deepest secrets, proving that sometimes the journey from science fiction to science fact begins with a single, spectacular illusion. While our journey through these 30 theories has taken us from the depths of quantum foam to the edge of the observable universe, the story of wormholes is far from over. In fact, some of the most exciting chapters are being written right now in laboratories and on supercomputers around the world. The focus of future research is shifting from pure mathematical speculation toward a more concrete, testable framework, aiming to find ways to probe these cosmic shortcuts indirectly and perhaps even find the first hints of their existence hidden in the data we're collecting today. This represents a monumental leap, moving the subject from the fringes of theoretical physics closer to the realm of empirical science, where ideas must face the ultimate judge: observation. One of the most promising frontiers is the ongoing effort to develop a complete theory of quantum gravity. For decades, wormholes have been primarily studied within the context of classical general relativity, but we know that to truly understand their stability and behavior, especially at the microscopic level, we must account for quantum effects. Research in string theory and loop quantum gravity is now actively exploring how quantum corrections modify the classic wormhole solutions. Scientists are running immense computer simulations to model how the fabric of spacetime might behave under the extreme conditions of a wormhole throat when quantum fluctuations are taken into account. The key question is whether these quantum effects naturally provide a repulsive force that could stabilize the throat, potentially reducing or even eliminating the need for the fantastical amounts of exotic matter required in purely classical models. Each new equation solved in this domain brings us a little closer to understanding whether the universe's own quantum rulebook might actually permit these structures to exist. Alongside these theoretical advancements, a global hunt for observational evidence is gaining sophisticated new tools. The Event Horizon Telescope, which gave us the first image of a black hole's shadow, is continually being upgraded with more telescopes around the world, increasing its resolution to unprecedented levels. Researchers are now developing detailed simulations of what the shadow of a wormhole would look like compared to that of a black hole. The presence of a traversable throat or the faint glow of light from a universe on the other side could create a unique and detectable signature within that dark circle. By comparing these theoretical templates with ever sharper images of objects like Sagittarius, a star, astronomers hope to one day spot an anomaly, a tiny deviation in the pattern of light that whispers of a tunnel instead of a pit. Furthermore, the burgeoning field of gravitational wave astronomy offers another powerful avenue for investigation. When the LIGO and Virgo observatories detect the ripples in spacetime from colliding black holes and neutron stars, they are measuring the precise way these massive objects warp the fabric of the cosmos before merging. Some physicists are now modeling the gravitational wave signal that will be produced by the collision of two exotic objects like boson stars or even hypothetical wormholes. The distinctive chirp and ring down of such an event would have a unique frequency and pattern, completely different from the signals we've observed so far. As our detectors become more sensitive, they may yet pick up a signal that doesn't match any known celestial object, opening the door to the possibility that we're listening to the vibrations of a spacetime tunnel snapping shut or the resonant frequency of a stable throat. On a much smaller but no less profound scale, tabletop experiments are seeking to test the principles that underpin wormhole physics. While we can't create a gravitational wormhole in a lab, scientists are using analogs to simulate their behavior. One fascinating approach involves quantum computers. Researchers have already used quantum processors to simulate the dynamics of a holographic wormhole, essentially creating a quantum system that behaves according to the same mathematical rules as a wormhole in a lower dimensional universe. This allows them to study concepts like information transfer through a tunnel and the effects of negative energy in a controlled, experimental setting. Other experiments are pushing the limits of metamaterials, artificially structured materials that can manipulate light in ways not found in nature, to create optical wormholes that can guide electromagnetic waves around an object, making it appear invisible. While not true gravitational wormholes, these experiments allow us to test the complex geometry and scattering effects that are central to the theoretical models, providing valuable insights that can feed back into the physics of the real thing. The ultimate goal of all this research is to move wormholes out of the realm of pure thought experiment and into the domain of tested science. It's a gradual process of connecting the dots, a slight anomaly in a telescope's image, a strange signal in a gravitational wave detector, a successful simulation on a quantum computer that matches a theoretical prediction. Each small discovery would narrow the possibilities, constraining the vast landscape of theories and guiding us toward a more complete understanding of whether these cosmic shortcuts are a physical reality. The path forward requires a synergy of immense imagination and meticulous observation, a combination that has always been the driving force behind our greatest leaps in understanding the universe. We may not be stepping through a stargate tomorrow, but for the first time in history, we are building the tools that might just allow us to prove that the gates are actually there. Now we arrive at our final theory, one that scales up this incredible concept to its absolute limit, connecting the fate of wormholes to the ultimate destiny of the entire cosmos. For all our talk of interstellar travel and time machines, these could be mere footnotes in a far grander story, where wormholes play a role in the birth, death, and rebirth of universes themselves. This idea forces us to confront the bleakest prediction of modern cosmology, the heat death of the universe, and asks if a network of tunnels might offer a spectacular escape hatch or even a form of cosmic immortality. The heat death is the universe's predicted final state, a fate of quiet, cold, and eternal equilibrium. As the cosmos continues to expand and accelerate, driven by dark energy, galaxies will be pushed so far apart that the night sky will become truly black. Stars will burn through their fuel and die one by one until no new ones are born. Eventually, even the most massive black holes will slowly evaporate away via Hawking radiation, leaving behind a sparse, dilute soup of fundamental particles and radiation, spread so thin that the temperature approaches absolute zero. In this state, no work can be done, no structure can form, and no meaningful event can ever occur again. It is the end of time in any practical sense, a static, silent eternity. For any conscious beings remaining, it would be an inescapable prison of nothingness. This is where wormholes present a radical and hopeful alternative. Some theoretical models suggest that a universe heading toward heat death might not be a closed system. If a web of stable wormholes permeates the cosmos, it could provide a conduit, a way for information and even matter energy to escape the dying confines of our expanding space and be injected into a younger, more vibrant universe. Imagine our universe as an old, decaying city whose power grid is failing. Wormholes could act as cables, siphoning the last remaining useful energy out and transferring it to a newly built city next door, giving it a jump start. In this scenario, the eventual heat death of our universe wouldn't be the absolute end. It would be a transition phase, a slow leaking of its residual energy into another reality, allowing something new to grow from the ashes of the old. An even more profound idea posits that wormholes aren't just escape routes, but are actually the engines of cosmic reproduction. This theory is deeply intertwined with the concept of a black hole universe. We discussed earlier how some models in loop quantum gravity suggest that the interior of a black hole might not be a singularity, but a quantum bounce that leads to a new, expanding universe on the other side. In this view, every black hole in our cosmos could be the birthing event for an entirely new universe with its own physical constants and laws. The wormhole, or Einstein-Rosen Bridge, is the umbilical cord connecting the parent universe to its child. This creates a breathtaking vision of a multiverse that isn't just a static collection of parallel worlds, but a growing, evolving fractal tree of life. Our own universe, with its hundreds of billions of galaxies, each containing billions of black holes, would be an impossibly fertile progenitor, giving birth to a staggering number of offspring universes. And those daughter universes would themselves form black holes, creating grand universes, and so on, ad infinitum. The wormhole is the crucial link in this cycle, the mechanism by which the information and structure of one universe is passed on to seed the next. It transforms the cosmos from a single, doomed entity into a self-perpetuating system, where death in one branch gives rise to life in another. This leads to a fascinating and almost philosophical implication about the fine-tuning of our universe. Why do our physical constants seem so perfectly calibrated to allow for galaxies, stars, planets, and ultimately, life? If this cosmic reproduction cycle is real, then a form of natural selection might be at play. Universes that have physical laws conducive to forming many black holes which require massive stars, which in turn require the specific physics we observe, are the ones that are most reproductively successful. They produce the most offspring. A universe with weak gravity or different nuclear forces might form few or no black holes, rendering it sterile, a dead end in the great cosmic tree. Our universe isn't fine-tuned for us. We are simply a byproduct of a universe that is fine-tuned for prolific reproduction via black holes and wormholes. We live in a cosmos that is very good at making babies. Ultimately, these theories elevate the wormhole from a potential tool for a single species to the status of a fundamental architectural feature of reality. They suggest that the cosmos might be inherently connected, not just in space, but in time and across generations of existence. The wormhole could be the thread that weaves the tapestry of the multiverse together, ensuring that even as individual universes flame out and fade to black, the grand story of existence continues forever, giving rise to an infinite series of new beginnings. It's a powerful, hopeful counterpoint to the silence of heat death, proposing that the universe we call home might be just one chapter in an endless, evolving epic of creation. From the silent, mathematical birth of the Einstein-Rosen Bridge to the cosmic scale engineering of harnessing dark energy, our journey through 30 incredible theories has revealed a universe far stranger and more interconnected than we ever imagined. We've stood at the edge of a rotating Kerr wormhole, peered into the quantum foam from which reality itself may be woven, and pondered the possibility that every black hole might secretly be a gateway to another cosmos. We've grappled with paradoxes that challenge the very fabric of cause and effect, and dared to dream of a future where the vast distances between stars are rendered meaningless by a network of tunnels stitched into the very architecture of spacetime. So where does this leave us? The chasm between these breathtaking theories and practical reality remains vast. The energy requirements are still astronomical, the exotic matter elusive, and the stabilization techniques the stuff of far future speculation. Yet, for the first time in human history, we are not just dreaming about these possibilities, we are actively hunting for them. The Event Horizon Telescope is imaging the shadows of massive objects. Gravitational wave observatories are listening for the unique chirp of exotic collisions, and quantum computers are running simulations of holographic wormholes in their processors. We are moving from pure mathematical fantasy into the realm of observational science, testing the limits of these ideas and inching closer to answering the ultimate question. Are wormholes a genuine feature of our universe, or the most beautiful dead end in theoretical physics? The true magic of this exploration lies not in a definitive answer, but in the questions themselves. Each theory, from the elegant ER equals EPR connection to the primordial wormholes woven into the cosmic microwave background, expands our understanding of what might be possible. They force us to rethink the nature of reality, time, and our place in the cosmos. This isn't just about building a stargate, it's about comprehending the deepest workings of existence. We are collectively piecing together a puzzle of unimaginable scale, and every new idea, no matter how speculative, adds another piece to the picture. Now, we want to hear from you. Which of these theories completely reshaped your view of the universe? Was it the revelation that quantum entanglement and wormholes might be the same phenomenon, the terrifying and thrilling potential of a time-traveling Morris-Thorne ring? Or the awe-inspiring idea that our entire universe could be one of many in a cosmic family tree connected by black hole umbilicals? Let us know in the comments below. We're just as fascinated by this conversation as you are. If your curiosity about cosmic mysteries is as infinite as the universe itself, make sure to subscribe and hit the notification bell. We're just getting started on this journey, and there are so many more wonders to explore, from the enigmatic nature of dark matter to the mind-bending possibilities of other dimensions. The cosmos is the greatest story ever told, and we're here to explore every chapter of it together. Thank you for joining us on this incredible adventure through the gate